There is an answer to the Fermi paradox, not a theory, not a guess, not one possibility among many equally weighted options sitting on a shelf waiting for someone to choose their favorite. An answer, the kind that holds together when you press it from every direction, when you run the numbers against it, when you drag it into the light of modern astronomy and ask it to survive contact with actual data. It holds. Most researchers who have spent serious time on this problem already know what that answer is. Some will say it plainly. Most will not, and the reason they stay quiet is not because the answer is uncertain. It is because the answer is specific, and the specificity is what makes it unbearable. It points at something precise about where we are right now, about what kind of civilization we have become, and about what that typically means for civilizations that reach this particular threshold. Right now, there are roughly 30 serious hypotheses that attempt to explain why the cosmos stays silent. We are going to work through all of them. We will start with the ones that let you sleep, then move to the ones that resist easy dismissal, and finally arrive at the ones that most people stop reading before they reach. By the time the investigation closes, only one explanation is still standing, the one that virtually nobody wants to be true. To understand why that answer lands the way it does, you first need to understand the real question underneath the famous one. Not the poetic version, not the philosophical meditation, but the raw physical question that a man named Enrico Fermi asked over lunch in the summer of 1950 and could not stop turning over in his mind. Los Alamos, New Mexico, summer of 1950. A group of physicists sitting together at midday. The newspapers that week were full of stories about flying saucers, which was a subject the serious scientific community generally treated with polite distance. The conversation drifted in that direction anyway, the way conversations do when the workday briefly suspends itself. Fermi listened, and then, somewhere between bites, he asked a question that sounded absurdly simple. He said roughly, "Where is everybody?" His colleagues laughed first, then they thought about it, then the table went quiet. The question sounds like something a child asks on a clear night when someone points at the stars and explains that some of them might have planets. But when you actually press the mathematics against it, when you run the numbers and then stand the numbers against the emptiness of the sky, it transforms into something that does not let go. It becomes an obsession. It becomes a career for some people and a sleepless night for others, and a quiet dread for those who think about it long enough. Here is the physical reality behind the question. In 1961, an astronomer named Frank Drake sat down at the National Radio Astronomy Observatory in Green Bank, West Virginia, and wrote an equation. He was preparing for a small conference, and he wanted a structured way to think about how many technologically advanced civilizations might currently exist in our galaxy and be actively producing detectable signals. The equation he wrote multiplied together a chain of rates and probabilities. The rate at which new stars form, the fraction of those stars that have planets, the fraction of those planetary systems that develop habitable worlds, the fraction of those worlds where life actually starts, the fraction where life eventually produces intelligence, the fraction where intelligence builds detectable technology, and the average length of time such a civilization remains detectable before it goes quiet for whatever reason. Multiply those numbers together and you get an estimate of how many civilizations we might be able to detect right now. When Drake first ran through the equation, most of the terms were essentially guesses. We had no confirmed planets around other stars. We did not know how often chemistry crosses the threshold into biology. We were working almost entirely in the dark, building estimates from analogy and theory and hope. We are no longer working in the dark. The Kepler Space Telescope operated from 2009 to 2018. During that time, it stared at a fixed patch of sky containing roughly 150,000 stars and watched for the tiny dimming events that happen when a planet crosses in front of its star. It confirmed more than 4,000 exoplanets and implied the existence of billions more. What it found completely overhauled the first several terms of Drake's equation. Planets are not rare, they are ubiquitous. Nearly every star in the galaxy appears to host at least one planet, and many host several. The fraction of stars with planetary systems turned out to be close to 1, which is not what anyone conservatively assumed before the data arrived. Rocky planets in the temperature range, where liquid water is possible, are not common in an everyday sense, but they are not vanishingly rare either. When you run Drake's equation with the numbers the Kepler data actually supports, even using very conservative estimates for the biological and social variables we still cannot measure, the result keeps coming out in the thousands or millions of technological civilizations within the Milky Way alone. Right now, potentially broadcasting, potentially producing the kinds of electromagnetic and thermal signatures that our instruments should be able to detect. And the Milky Way is just one of an estimated 2 trillion galaxies in the observable universe. By the math, the cosmos should be loud. It should be saturated with signals and technosignatures and the byproducts of large-scale engineering. It should be full of the waste heat and the electromagnetic leakage and the chemical imbalances that intelligent energy-using civilizations leave behind without even trying. We should have picked something up by accident by now, the way you might overhear a conversation through a thin wall without anyone intending to broadcast it. In 1977, a researcher named Jerry Amen was doing exactly the kind of patient, unglamorous work that characterizes most of science. He was going through computer printouts from Ohio State University's Big Ear radio telescope, scanning columns of numbers that represented signal intensities at various frequencies. This was 1977. Everything was still on paper. He was running his finger down the columns, and he found something. A narrowband signal centered almost precisely on 1420 MHz, the hydrogen line, the exact frequency that theoretical physicists had long argued an intelligent civilization would most naturally choose for long-distance signaling, because hydrogen is the most abundant element in the universe, and its resonance frequency would be a natural common reference point. The signal lasted 72 seconds, the maximum duration the fixed telescope could observe any given point in the sky as the Earth rotated. It registered so far above the background noise that Amen circled it on the printout and wrote one word next to it in the margin. Wow, that was August 15, 1977. Since that night, the sky around that signal's origin has been checked hundreds of times with multiple telescopes. The signal never came back. It has been nearly half a century of follow-up observations. Nothing. So here is the situation. One anomaly in 65 years of dedicated searching. One signal that appeared once, lasted 72 seconds, and vanished completely. Against the backdrop of mathematics that says the sky should be screaming at us. That is the Fermi paradox stripped of poetry. It is not a question about whether we are spiritually alone in the universe. It is a contradiction between two things, a calculation that predicts an observable result and a sky that refuses to produce that result. It is a mismatch between expected and measured, which in science is not a mystery to be appreciated. It is a problem to be solved. Before we go any further, let us know in the comments where in the world you are watching from and what time it is there. Now settle in. We are going to build this investigation layer by layer. We are going to start with what the sky should look like if physics is fair and civilizations are common. Then we are going to examine what it actually looks like. Then we are going to go through the serious hypotheses one by one and test them against the data, against the logic, against each other. The ones that cannot survive contact with modern knowledge will be eliminated. The ones that survive will carry increasing weight. And by the end, when only one explanation is left standing, you will understand exactly why it is the one that nobody wants to talk about. The Milky Way is approximately 13.5 billion years old. Its oldest stars formed not long after the Big Bang, in an early universe that was already running chemistry and gravity and nuclear physics by the same rules that govern our own sun today. The galaxy has been making stars and planets for most of that time, continuously, across hundreds of billions of stellar nurseries scattered through its spiral arms and central bulge. It has been doing this long enough that civilizations far older than ours are not just theoretically possible. They are, by any straightforward reading of the math, statistically expected. Consider what that age implies. If a civilization arose on another world just 1 million years before we did, which is a blink in galactic timescales, they would have had a million-year head start on everything we are doing. 1 million years ago, our ancestors were hominids in Africa. We went from stone tools to radio telescopes in roughly 200,000 years. A civilization with a million-year head start on that trajectory would be so far beyond us in capability that the comparison barely makes sense. They would be to us roughly what we are to the microbes in our gut, and 1 million years is nothing. 5-billion-year-old stars host planets that have had 5 billion extra years to run their experiments in chemistry and evolution and intelligence. The galaxy has had time to generate civilizations millions of years ahead of us, not just thousands. And yet the sky is quiet, no signals, no megastructures, no infrared excess from stellar-scale engineering. No evidence of the kind of energy use that a civilization operating at scale for even a few million years would be physically incapable of hiding. No stray transmissions picked up accidentally. No obviously artificial patterns in any band of the electromagnetic spectrum. Nothing that resists a natural explanation. That is the full shape of the paradox. It is not just about signals. It is about physical consequences. Technology uses energy. Energy use has thermodynamic consequences. Thermodynamic consequences leave marks on the universe that telescopes can read. A civilization operating at the scale of its home star system for a million years would be visible from the outside in ways that have nothing to do with whether they want to talk to us. Their waste heat would radiate into space regardless of their intentions. Their chemistry would alter their planet's spectrum, whether or not they cared about advertising their presence. The absence of these marks across a galaxy that has had billions of years to accumulate them is not a minor puzzle. It is a deep structural contradiction between expectation and measurement. Let us build the quantitative backbone of that contradiction carefully, because the strength of the paradox depends on the strength of the underlying numbers, and those numbers have changed dramatically in the last 2 decades. The Drake equation's early terms, the ones about star formation and planet occurrence, are no longer estimates. They are measurements. The rate of star formation in the Milky Way is well constrained by observations of stellar populations and gas dynamics. Roughly 1 to 3 new stars form every year in our galaxy, a pace that has continued for billions of years and has already produced somewhere between 200 and 400 billion stars currently shining across the disk. The fraction of those stars that host planets is, as Kepler demonstrated beyond serious dispute, close to 1, not half, not a quarter, close to 1. Planets are the default output of star formation, not a special circumstance. The distribution of those planets matters enormously for the next terms. Small rocky planets in the temperature range consistent with liquid water are not the most common type, but they occur at a rate that, when multiplied across hundreds of billions of stars, produces a staggering absolute count. Some estimates put the number of potentially temperate rocky worlds in the Milky Way at 10 billion or more. Others put it higher. Even the conservative end of the range is difficult to wrap intuition around. 10 billion places where the temperature and chemistry might in principle support liquid water on a surface. The raw number of venues is simply enormous. So the first several terms of Drake's equation, the ones we can now measure, push the expected count of technologically active civilizations upward with considerable force. The pressure falls entirely on the later terms, the ones about life, intelligence, technology, and longevity, and those terms are where the genuine scientific debate lives. Those terms are also where the great filter hides, but we are not there yet. For now, stay with the basic quantitative point. Even under conservative assumptions for the unmeasured terms, the math keeps yielding large numbers, even if life arises on only 1 in 1,000 habitable worlds. Even if intelligence emerges on only 1 in 1,000,000 biospheres. Even if technological civilizations are rare by any standard, the galaxy is so large and so old that the expected number of civilizations that should currently exist and leave detectable traces remains non-trivially above 0. The silence is not what a naive application of the math predicts. The silence is the problem. There's a version of this that people sometimes try to dissolve by pointing at the distances involved. Space is very big, the argument goes. Signals attenuate. Civilizations that are far away are hard to detect. This is true as far as it goes, but it does not go nearly far enough to dissolve the paradox. The paradox is not only about receiving deliberate signals from distant civilizations. It is about the absence of any detectable consequence of large-scale intelligence across the observable universe. A civilization that has been operating at the energy scale of its star system for 1,000,000 years does not need to be transmitting a beacon for us to detect it. Its waste heat alone would produce an infrared signature detectable by modern instruments out to significant distances. A civilization that has spread beyond its home system, even modestly, even slowly, would begin to alter the spectral properties of multiple stars in a way that stands out against the background. The absence of these signatures in our infrared surveys is itself a data point. It constrains how common and how large-scale and how long-lived technologically active civilizations can be, and the constraints are uncomfortable. The wow signal is worth dwelling on for a moment, not because it resolves anything, but because it illustrates exactly how desperate the data situation is. One signal, in nearly half a century of listening, that stands out enough to get a human's attention. One event that matches the profile we would expect from a deliberate beacon, and then nothing. It never returned. Every subsequent search of that patch of sky has been disappointing in the most ordinary sense of the word. There is nothing there. The most exciting data point in the history of the search for extraterrestrial intelligence is a single observation that we cannot confirm and cannot explain and cannot build on. That is the dataset. One anomaly against 65 years of silence. The disproportion between those two things, between what the math predicts and what the instruments detect, is the engine driving everything that follows in this investigation. Before we examine the hypotheses, we need to be clear about what the silence actually rules out and what it does not, because the strength of each proposed explanation depends entirely on this. The silence is not an absolute measurement. It is a constrained one, and constraints are not verdicts. SETI, the search for extraterrestrial intelligence, has been operating in some form since Frank Drake pointed a radio dish at 2 nearby sun-like stars in 1960. In the 65 years since then, the search has expanded enormously in some dimensions and remains severely limited in others. Modern SETI uses large arrays of radio dishes, sophisticated signal processing, and automated scanning across enormous swaths of sky. It has covered millions of stars and logged billions of frequency channels. It has also, in its more recent incarnations, begun scanning for optical laser pulses, which some researchers argue might be a more efficient interstellar communication medium than radio for highly advanced civilizations. What has it found? In the radio bands, the honest answer is nothing compelling. There are anomalous signals, things that cause researchers to look twice, but nothing that has survived the scrutiny of follow-up observation, nothing that repeats. Nothing that resists a mundane explanation after careful analysis. In the optical bands, the results are similarly empty. The search for laser pulses has returned nothing that requires an intelligent origin. This sounds decisive until you think carefully about the scope of what has actually been searched. The Milky Way contains somewhere between 200 and 400 billion stars. SETI has examined, in any systematic sense, a tiny fraction of them. Even accounting for wide-field surveys that cover large portions of the sky without dwelling on individual targets, the depth and continuity of the search are severely limited. A civilization transmitting a narrowly beamed signal, like a lighthouse rather than a lamp, would only be detectable during the fraction of time when that beam sweeps past Earth. If the beam sweeps past once every century, and our monitoring of any given direction is intermittent, we might miss it entirely across the whole history of the search. A civilization transmitting only briefly in cosmic terms might have been shouting in the 1800s and gone silent before we built receivers. A civilization transmitting in bands we have not thought to monitor would be invisible to our instruments regardless of signal strength. The WOW signal itself illustrates the detection challenge perfectly. It appeared once, lasted as long as the geometry of the observation allowed, and never recurred in any follow-up. If it was a genuine artificial signal, we have no way to know whether it was ever repeated, because the follow-up coverage of that region is finite and our instruments change over time. We might simply have missed the repeats, or there were no repeats, which tells a different story. Either way, we are left with one data point and no way to interrogate it further. So the silence is real, but it is not the silence of a perfectly complete search. It is the silence of a search that has covered an enormous amount of sky in some dimensions and a surprisingly small amount in others. That nuance matters when evaluating hypotheses, because some hypotheses can hide a civilization from our current search methods much more easily than others. What the silence does rule out is the loud and careless end of the possibility space. Civilizations transmitting omnidirectionally at high power for long periods of time across radio or optical frequencies would be detectable across significant portions of the galaxy with our current instruments. The absence of any repeatable detection from any direction constrains the density of such civilizations to be extremely low, possibly zero in our galactic neighborhood. It does not rule out quiet civilizations, focused beam civilizations, or civilizations transmitting in modes we have not considered. But it does put real pressure on the naive expectation that the universe should be producing obvious, detectable signals in every direction. The infrared constraint is in some ways more powerful, because it is less about communication choices and more about physical consequences. The WISE and IRAS infrared surveys have mapped the entire sky at multiple wavelengths sensitive to the thermal emission that engineering at stellar scales would inevitably produce. The results show dust, star formation regions, galaxies, and the expected thermal signatures of ordinary astrophysical processes. What they do not show is a population of stars surrounded by the smooth, cool infrared excess that would result from extensive energy harvesting megastructures. Some anomalous infrared sources exist, and some have been investigated as potential candidates, but none have survived scrutiny as genuine engineering signatures. The infrared sky looks natural, and the naturalness of it is part of the problem. A civilization that has been harvesting a significant fraction of its star's energy for even 100,000 years would produce a distinctive spectral signature. The star's visible light output would decrease as collectors intercepted it, and the intercepted energy would be re-emitted at lower temperatures as waste heat, producing a mid-infrared glow that would stand out against the background. This is not a subtle effect at high coverage fractions. It is a large, measurable deviation from expected stellar spectral energy distributions, and the infrared surveys have been sensitive enough to detect it if it were common. The fact that the infrared sky looks overwhelmingly natural, with every bright source having a plausible astrophysical explanation, constrains large-scale stellar engineering to be either very rare, very recent, or very cleverly hidden. These constraints together define the shape of the problem we are investigating. The math says expect detectable civilizations. The instruments say detect nothing compelling. The gap between those two statements is the Fermi paradox, and it has survived 65 years of improving technology. Every time our instruments get better and our search broadens, the silence becomes a more precise measurement rather than a less precise one. That is the direction this has been moving for 6 decades, not toward resolution, but toward sharper constraint. There is a subtler version of the paradox that does not depend on signals at all, and it is arguably more disturbing than the radio silence. Imagine the simplest possible expansion scenario. A civilization decides to send probes to other star systems. Not colonies, not people, just self-replicating machines carrying instructions to arrive, gather local materials, manufacture copies of themselves, and send those copies on to the next set of stars. This is not Star Trek technology. It is at its core an engineering extension of processes we already understand: automation, replication, and directed movement. The physics does not require faster-than-light travel or exotic energy sources. It requires patience, and time is the one resource the galaxy has in abundance. At even 1% of the speed of light, which is far slower than the exhaust velocity of proposed nuclear pulse propulsion concepts and requires no new physics, a probe crosses the distance from one star to a neighboring one in a few hundred years. From there it replicates and sends copies to the next stars. The wave front of this expansion moves outward at a fraction of light speed, but it never stops and it compounds. The entire Milky Way, 100,000 light-years across, can be traversed by such a wave front in a few million years at this pace. 10 million years if the probes are cautious and take long breaks between hops. 10 million years sounds like a long time in a galaxy 13. 5 billion years old, 10 million years is less than 1/10 of the available time. If any civilization anywhere in the Milky Way started this process at any point in the galaxy's history, even briefly, even half-heartedly, the wave front would have had time to complete the crossing and arrive everywhere, including here multiple times over. The fact that there is no obvious sign of such a wave, no probes detected in our solar system, no obvious artificial objects in near-Earth space or among the asteroids or in the outer solar system, is itself a remarkable absence. It is called the Hart-Tipler argument, and it sharpens the paradox considerably beyond the signal detection problem. You can object that perhaps such probes would be too small to detect. True, potentially. A probe the size of a basketball arriving in the outer solar system might well escape our notice. But a civilization that has been doing this for 1,000,000 years across the whole galaxy would leave behind not just invisible probes but accumulated infrastructure, mining operations, construction, waste heat from computation and energy use. Even minimally active probes need power, and power has thermodynamic consequences. A 1,000,000-year-old network of self-replicating probes spread across the galaxy would constitute a macroscopic presence that our surveys should catch, at least statistically, as a deviation from expected natural distributions. The fact that stellar populations and planetary systems and interstellar space all look as if they have been left entirely to their own devices is a piece of data. It is a negative result, but negative results are real results. The colonization timescale argument also does not require that a civilization wants to colonize in any traditional sense. It does not require conquest or empire or the aggressive spread of a single culture. It only requires that any civilization, for any reason, sends capable self-replicating technology beyond its home system. Scientific curiosity alone would be sufficient motivation. Insurance against local disasters would be sufficient. The desire to exploit abundant resources elsewhere would be sufficient. The motivations are plentiful, the physics is known, and the timescales allow for it many times over. The absence of any detectable consequence is therefore genuinely strange. This is where the paradox bites deepest. It is not just about messages. It is about physical consequences that accumulate over time. If technology persists and grows, it leaves marks that are increasingly hard to hide. The galaxy should contain at least the fingerprints of one old civilization, maybe its infrastructure, maybe its waste heat, maybe its rearranged stellar populations. Instead, the galaxy looks pristine. It looks as if intelligence has never had the opportunity or the inclination to scale up and leave durable traces. That is the problem we are investigating, and it is a real problem, not a philosophical meditation. It is a mismatch between physical prediction and physical measurement, and it demands a physical answer. We are going to examine the serious hypotheses in order of how comforting they are, beginning with the ones that let you sleep. The first and most immediately comforting hypothesis is that we simply have not searched enough. The search space is enormous, the argument goes, and our instruments are primitive compared to what would be needed for a thorough survey. We have barely scratched the surface of the radio spectrum. We have not listened continuously to any direction. We have not monitored every star for years at a time. We have not searched every possible signaling modality. Give us another century and better tools, and maybe the sky will stop being quiet. This explanation has real merit, and it deserves to be taken seriously before being evaluated honestly. The search space for radio signals is indeed vast. The electromagnetic spectrum spans an enormous range of frequencies. A transmitting civilization could use any of them. Our searches have focused on bands that seem physically motivated, the hydrogen line, the hydroxyl line, and nearby frequencies that form the so-called cosmic watering hole, because these seem like natural meeting points that any scientifically literate civilization might choose. But that reasoning assumes we correctly understand what another civilization would consider natural or obvious, which is an assumption we have no real basis for making. An advanced civilization might consider our chosen frequencies as primitive, as we would consider smoke signals as a long-distance communication medium. The search space for non-radio technosignatures is even less thoroughly covered. Optical SETI searching for laser pulses is a relatively young field. The search for infrared signatures of megastructures is still in its early days. The search for artificially modified stellar spectra, for objects moving in ways that betray engineering, for chemical imbalances in planetary atmospheres, these are all young programs with limited track records. It is genuinely possible that we are missing something obvious because we have not yet looked in the right way. This argument can be quantified approximately, and when it is quantified, the picture is less comforting than the qualitative version sounds. Various researchers have tried to estimate what fraction of the plausible search space SETI has actually covered. The numbers depend on assumptions, but estimates often suggest that the completed radio search covers something like 1 part in a trillion of the total search space, accounting for all possible frequency bands, all possible signal types, all possible directions, and all possible durations. That sounds like we have barely started, and in some sense we have. But the fraction is misleading if it is not weighted by detectability. The signals most likely to be detected are the loud, omnidirectional, persistent ones, because they are the easiest to find regardless of when and how we search. A civilization broadcasting a beacon at high power across the whole sky for thousands of years would be detectable across large fractions of the galaxy with even our current instruments. The absence of any such signal, despite surveys that have covered the whole sky in multiple radio bands, constrains the density of those loud persistent beacons to be very low. We may not have searched everything, but we have searched the loud obvious part fairly well, and the loud obvious part is empty. The silence is not uniform across the search space, and the part that has been well searched is particularly significant. The infrared constraint makes the "we have not searched enough" argument even harder to sustain as a complete explanation. Infrared surveys are not limited by communication choices or signaling strategies. Waste heat is not optional for a civilization that uses energy at scale. The WISE survey covered the entire sky at 4 infrared wavelengths, with sensitivity sufficient to detect Dyson sphere-like constructs around nearby stars, and it found none that survive scrutiny. The Gaia satellite has provided extraordinarily precise measurements of stellar positions and proper motions across more than 1 billion stars, generating a data set that researchers can mine for anomalies that might indicate artificial structures. The anomalies found so far have conventional explanations. The sky, across many different observation strategies and many different physical signatures, looks natural. So the explanation that we have simply not searched enough is partially true, importantly true, and yet insufficient as a complete answer. It explains the null result in the radio domain reasonably well given the limitations of the search. It does not explain the infrared null result nearly as well. It does not explain the Hart-Tipler colonization argument at all, because that argument does not depend on us receiving a signal. And it does not explain why no civilization in the galaxy's long history has done something so obvious and so large that it shows up in passive sky surveys conducted with instruments we already have. We have not searched enough is a valid partial answer. It is not the complete answer. The paradox survives even after we take it seriously. The next family of explanations says that contact has not happened because of the physical constraints of interstellar communication and travel. Space is very big. Signals weaken with distance. Light speed imposes delays that make conversation essentially impossible across stellar distances. Perhaps civilizations exist, but the universe is so large and communication so difficult that we should not expect to have heard anything yet. The distance argument has genuine physical content. Radio signals do attenuate with the square of distance. A civilization transmitting at the power level of our most powerful radar installations would produce a signal detectable by our best current instruments only to a relatively modest distance, perhaps a few hundred light-years in the most optimistic scenarios. The Milky Way is 100,000 light-years across. On that scale, a few hundred light-years is a tiny neighborhood around our sun. If our nearest technological neighbors are several thousand light-years away, their leakage radiation, the kind that escapes unintentionally as a byproduct of ordinary use rather than deliberate broadcasting, would be below the threshold of detection with current technology. This is an honest point. We are not so arrogant as to expect that every civilization is broadcasting a beacon specifically designed to be detected by us. Leakage radiation from our own civilization has been escaping into space for about a century, and it is already below the detection threshold of any plausible instrument at even a few light-years distance, let alone tens or hundreds. We are not easy to find accidentally. Perhaps our neighbors are equally quiet in terms of unintentional leakage and equally uninterested in spending energy on beacons that might never be received. But the distance argument dissolves under pressure for the same reason the colonization time argument does. It only applies to communication. It does not apply to physical presence or to the thermodynamic consequences of large-scale activity. The infrared signature of a star-spanning civilization is not a signal that attenuates like a radio wave from a point source. It is a change in the star's spectral energy distribution, and that change is visible as long as the star is visible. We can detect the spectral properties of stars thousands of light-years away. We can also detect them hundreds of thousands of light-years away in companion galaxies. An infrared survey is not a communication experiment. It is a physical measurement, and physical measurements of stellar populations are not limited by whether anyone intends to transmit. The light-speed delay argument is real but similarly limited in scope. Yes, a civilization 100,000 light-years away could not have a conversation with us in any meaningful sense. The signal travel time would be 100,000 years in each direction, but the argument that this prevents detection does not follow, because detection does not require conversation. A civilization that has been expanding and engineering for millions of years would be visible not because it is talking to us, but because it exists, and physics is not optional. Its waste heat radiates regardless of whether it is responding to a signal we never sent. The big universe argument also has a specific quantitative failure mode. Even if communication is impossible across the full extent of the galaxy contains enormous numbers of stars within relatively small distances of each other. The nearest few thousand stars to the Sun are within a few hundred light-years, a distance that is not trivially small, but is not insuperably large for a civilization with advanced technology. A civilization 1,000 light-years away that has been operating for 1,000,000 years would have had ample time to propagate its technology across that distance multiple times, or to produce signals powerful enough to be detected at that range by instruments we could in principle build. Scaling the problem to the full galaxy makes the silence seem smaller. Scaling it to the local neighborhood, where detection should be easiest, makes it seem more acute. So the physical difficulty of interstellar communication is a real constraint that modifies what we should expect to detect. It does not resolve the paradox. The paradox is not primarily about whether we have received a letter from another star system. It is about why the universe does not show the thermodynamic and structural fingerprints of civilizations that have had billions of years to leave them. A softer version of the distance and difficulty arguments says that the timing is just off. We might be too early. The universe is young in the sense that it took a long time to build up the heavy elements needed for rocky planets and complex chemistry. The first generation of stars were almost entirely hydrogen and helium, with none of the carbon, oxygen, silicon, and iron that life as we know it requires. Those elements were forged in stellar interiors and scattered by supernovae, enriching the interstellar medium over billions of years. The first truly Earth-like rocky planets probably could not have formed until several billion years into cosmic history, when the metal content of the galaxy had built up sufficiently. Given that Earth itself is about 4–5 billion years old, and given that technological civilization appeared here after 4 billion years of biological evolution, the earliest possible civilizations anywhere in the universe probably arose only a few billion years before us. A few billion years sounds like a large head start. It is. The argument's force, however, depends on what a civilization can accomplish in a billion years, and the answer to that question, even by very conservative standards, is that they should be impossible to miss. A billion years is enough time to colonize the galaxy, many times over even at very slow expansion rates. It is enough time to restructure stellar energy budgets on scales visible across millions of light years. The timing argument does not dissolve the paradox. It adjusts the severity of the head start while leaving the fundamental contradiction intact. There is a version of the timing argument that says we are simply among the first, and that is why we do not see older civilizations. The galaxy has had perhaps one or two serious windows for technological civilizations so far, and we happen to be in the first cohort. This is a version of the rare Earth argument, which we will examine in detail, but it deserves a brief treatment here as a timing hypothesis. For this argument to work, it needs to explain not just why we are early, but why we are so early that no predecessor has had time to become detectable. The galaxy has been making sun-like stars for 10 billion years. Many of those stars have been gone through their life cycles and left planetary systems with multi-billion-year histories. If even one technologically capable civilization arose around one of those early stars, it has had an extraordinary amount of time to become visible. The timing argument can absorb this if it posits that the conditions for technological life were not in place until recently, that early epoch planets lacked something essential, perhaps heavy element diversity, or that early stellar environments were too energetically violent. These are real constraints that planetary scientists take seriously, but they push the timing argument into the territory of rare Earth, where it becomes a claim about the specific prerequisites for complex life rather than a simple temporal offset. We are too early to have heard from anyone remains a genuinely open possibility. It is not, however, a comfortable resolution to the paradox, because it requires careful bookkeeping about what too early actually means in a galaxy that has been running its chemistry for 13.5 billion years. The hypothesis that the universe is simply teeming with life, but that life is mostly microscopic and silent, deserves careful treatment, because it is both plausible and insufficient. Microbial life, if it exists beyond Earth, would be enormously interesting biologically and philosophically. The discovery of a second origin of life anywhere in our solar system would be one of the most important scientific results in human history, completely rewriting our understanding of how common biology is in the universe. But microbial life, no matter how abundant, does not resolve the Fermi paradox in the form that is most compelling. The version of the paradox that microbial abundance addresses is the one that asks why we have not found any life at all anywhere, and answering that version with maybe microbes are common is a reasonable response to that narrower question. But the version of the paradox that bites hardest is not about life. It is about technologically advanced civilizations that have had time to become physically prominent in the galaxy. Microbes on Mars or in Europa's ocean say nothing about the absence of Kardashev-type II civilizations whose waste heat should be visible in infrared surveys. The two questions are almost entirely decoupled. In fact, as we will explore in detail, abundant microbial life combined with silence from advanced civilizations tells a particularly dark story. It implies that the bottleneck is not at the beginning of the chain, where chemistry becomes life, but somewhere later in the chain, where life becomes mind or mind becomes technology or technology becomes durable. If biology is easy, the great filter is probably not behind us. And if the great filter is not behind us, it is ahead of us. That is the direction in which abundant, simple life points, and it is not a comforting direction. The microbial universe hypothesis is therefore a partial answer to a limited form of the paradox, and it actively worsens the prospects for the rest of the explanation. We will return to this point in detail when we examine the great filter. Now we come to the hypothesis that is simultaneously the most comforting and the most difficult to fully validate, the idea that intelligent life is extraordinarily, improbably rare, not just somewhat rare, vanishingly rare, so rare that despite hundreds of billions of stars and billions of years, the galaxy may never have produced more than one technological civilization, and we might be it. This hypothesis has a name. Peter Ward and Joe Kirschvink, building on work by many others, gave it the name Rare Earth. The core claim is that the chain of events that produced technological intelligence on this planet was not a typical sequence of events that many worlds reliably replicate. It was an extraordinary conjunction of geological, astronomical, chemical, and biological improbabilities, each one individually unlikely and collectively so improbable that replication elsewhere is essentially impossible even across cosmic scales. To evaluate this claim properly, we need to take it apart step by step, because it is not a single claim. It is a chain of linked subclaims about each step in the sequence from planet formation to radio transmitters, and the chain is only as strong as its weakest link. Start with the planet itself. Earth is not simply a rocky world in the habitable zone. It is a specific kind of rocky world with a specific geological history that Rare Earth argues was essential to producing complex life. The planet has active plate tectonics, which recycles carbon and maintains a long-term climate regulation through the carbonate silicate cycle. This cycle works roughly like a planetary thermostat. When temperatures rise, weathering accelerates and draws carbon dioxide out of the atmosphere into rocks, cooling the climate. When temperatures fall, weathering slows and volcanic carbon dioxide accumulates, warming the climate. Over geological timescales, this feedback has maintained liquid water on Earth's surface despite the sun's gradual brightening over billions of years. Without plate tectonics or something functionally equivalent, this thermostat may not function reliably, and long-term climate stability becomes uncertain. The problem is that plate tectonics is neither simple to produce nor easy to detect on other worlds. It depends on the rheological properties of the mantle, the water content of the lithosphere, the thermal budget of the interior, and the mechanical properties of the crust. Small changes in any of these can tip a planet toward the stagnant lid configuration that Venus appears to exemplify, where a single rigid crust floats over the mantle without subducting, disrupting the carbon recycling loop and potentially allowing climate to drift in dangerous directions. Whether plate tectonics is common or rare among Earth-sized worlds is not yet known observationally. We can estimate interior temperatures from density measurements of exoplanets, but we cannot directly measure mantle dynamics across interstellar distances. The first rare Earth requirement is plausible but not well constrained by current data. Then there is the matter of Earth's large moon. The moon is unusually large relative to Earth's size, the product of a catastrophic collision between the proto-Earth and a Mars-sized object early in the solar system's history. This giant impact hypothesis is well supported by the chemical similarities between Earth and lunar rocks. The moon influences Earth's axial tilt, moderating the obliquity variations that would otherwise swing through much larger ranges over millions of years, potentially disrupting the climate more severely. The moon also drives tides that may have been important in the early evolution of coastal ecosystems and may have influenced the timing of Earth's rotation rate, with consequences for atmospheric dynamics. The rare Earth argument treats the moon as a stabilizing factor that many worlds would lack, particularly because the giant impact that created it was a contingent and possibly rare event. The counterargument is that the stabilizing role of the moon may be exaggerated, that some recent simulations suggest Earth's obliquity might be at least partially self-regulated by other mechanisms, and that very different kinds of moons, or no moon at all, might allow for stable enough climates in other configurations. The necessity of a large moon for complex life is actively debated among planetary scientists, and the debate has not resolved. The presence of Jupiter in our solar system is another rare Earth factor, though the story is more complicated than the popular version. The popular claim is that Jupiter acts as a gravitational shield, sweeping up or deflecting comets and asteroids that would otherwise rain down on Earth, reducing the impact rate and thus giving life more uninterrupted time to develop complexity. The reality is that Jupiter's gravitational influence does both. It can deflect dangerous impactors away from the inner solar system, but it can also perturb bodies from the asteroid belt and from the outer solar system onto Earth-crossing orbits. The net effect on Earth's impact rate is not obviously protective in all dynamical configurations. Early Jupiter may have been important in shaping the solar system's architecture, and its current position may indeed reduce certain categories of impacts, but the claim that a Jupiter-like giant is essential to complex life requires more specific modeling than the simple shield narrative implies. Even accepting all of these planetary requirements as real, the rare Earth hypothesis then faces the much harder task of explaining the biological side of the chain, the emergence of the eukaryotic cell, the development of multicellularity, the evolution of intelligence capable of cumulative culture, and the specific path to technology. Each of these steps has its own probability under the rare Earth framework, and the multiplication of those probabilities is where the hypothesis does its most important work and faces its most serious challenges. The emergence of the eukaryotic cell is the most biologically compelling of the rare Earth bottlenecks. For roughly the first 2 billion years of life on Earth, all organisms were prokaryotes, cells without nuclei or complex internal organization. The jump to eukaryotic cells, cells with nuclei, mitochondria, and complex internal architecture, appears to have happened once in Earth's history, approximately 2 billion years ago. The widely accepted mechanism involves the endosymbiotic merger of two distinct prokaryotic lineages, an archaean host engulfed an alpha protobacterium that became the mitochondrion rather than being digested. This merger provided the eukaryotic cell with an extraordinary energy production advantage, enabling the much more complex biochemistry that underlies all complex multicellular life. The rare earth argument treats this as a nearly impossible accident. The two cell types had to encounter each other. The host had to fail to digest the guest. The guest had to provide metabolic benefits rather than toxicity. Gene transfer between the two had to stabilize over long time scales, and the resulting hybrid had to survive and proliferate in competition with the already extremely successful prokaryotic world. The argument that this happened exactly once in 2 billion years of intensely competitive microbial life is taken as evidence that it almost never happens. The counterargument is that we have one data point, and one data point is not enough to establish probability. The merger might have happened several times and been lethal most times, or it might have happened only once because the ecological conditions for it were narrow and only occasionally appeared. The fact that it took 2 billion years might reflect the time required for the right conditions, not the time required by random search. Evolution does not explore all possibilities simultaneously. It explores the ones that are locally accessible, and the ecological and chemical conditions that made the Archaeobacterium merger possible may have taken 2 billion years to assemble on Earth regardless of the intrinsic probability of the merger itself. The atmospheric oxygen story is the clearest evidence that planetary conditions, not just pure luck, govern the pace of biological innovation. The Great Oxidation Event around 24 billion years ago was not simply a biological event. It was a planetary phase transition driven by the interplay of biological oxygen production by cyanobacteria, the chemical capacity of the ocean and crust to absorb that oxygen as it was produced, and the long-term geological processes that reduced the sink capacity. Oxygen accumulated in the atmosphere only when the production rate consistently exceeded the sink rate, which required not just the evolution of photosynthesis, but the saturation of geological oxygen sinks over billions of years of ongoing burial of organic carbon. Complex animals emerged only after a second rise in atmospheric oxygen in the Neoproterozoic, hundreds of millions of years after the first. The timeline suggests that biology was, in a sense, waiting for the planet to catch up. If that is the right interpretation, then the delay in complex life was not a measure of biological improbability, but a measure of planetary geochemistry progressing at its own pace. On a different world with different geology, the same sequence might proceed faster or slower, depending on the planet's volcanic activity, its plate tectonic regime, its mantle redox state, and its ocean chemistry. None of those are as narrowly constrained as rare earth would need them to be to make the argument fully convincing. The rare earth hypothesis is at its most powerful and its most difficult to test simultaneously. It can always point to the one data point of Earth and argue that each step looks contingent, each junction looks improbable, and each requirement looks specific. And it cannot easily be falsified because we do not yet have a second data point against which to compare. The discovery of complex multicellular life anywhere else in the universe would essentially end the debate in favor of the hypothesis being wrong, or at least much less right than its strongest proponents claim. The discovery of abundant simple microbial life, but no complex life, would strengthen it considerably for the reasons already mentioned. We are waiting on data that current technology cannot easily deliver. What we can say is this: rare earth is a serious, internally consistent hypothesis that many planetary scientists and evolutionary biologists take seriously. It may be correct, it may not be correct. But even if it is correct in all its details, it faces a quantitative challenge that it cannot entirely evade. The galaxy is so large and so old that even an extraordinarily small probability of technological life per star, when multiplied by hundreds of billions of stars and billions of years, can still produce a non-zero expected count of civilizations with sufficient time to become physically prominent. To fully dissolve the paradox with rare earth alone requires pushing the probability to such an extreme that it starts to feel like special pleading. And special pleading in a scientific investigation is a red flag. Rare earth is the first serious answer. It is comforting because it requires no predator and no catastrophe and no trap. It asks only that we accept we are extraordinarily lucky. That is an emotionally bearable conclusion. It is also a conclusion that the next chapters of this investigation will put under increasing pressure, because the sky is quiet not just in the radio bands, but in the infrared and in the colonization and in the thermodynamics, and rarity alone must absorb all of that silence simultaneously. Now let us take the full measure of where we are before moving into darker territory. We have established that the paradox is real and quantitative, not philosophical. We have shown that the silence is measured across multiple independent lines of evidence: radio searches, infrared surveys, the absence of colonization signatures, and the pristine appearance of stellar populations. We have examined and given honest credit to the hypothesis that we simply have not searched enough, concluding that it partially accounts for the radio silence, but does not account for the thermodynamic and physical evidence. We have examined the distance and timing arguments and found them insufficient as complete explanations. We have taken the rare Earth hypothesis seriously and found that it is genuinely possible, perhaps even more likely than naive optimism would predict, but that it faces a numbers problem that it cannot fully resolve. The honest position at this stage of the investigation is that none of the comfortable explanations survive intact. They all have merit, they all deserve to be considered, but they all leave residual tension with the data residual silence that they cannot fully absorb. Something more is needed. The something more is where the investigation gets uncomfortable. If civilizations are not as rare Earth requires them to be, then they must be failing. Something must be happening to them. Something that reliably prevents them from becoming the kind of long-lived, energy-intensive, physically prominent presences that infrared surveys and colonization, timescale arguments say should be visible. Something that hits civilizations at a predictable stage in their development and removes them from the count before they accumulate the kind of presence that would be hard to miss. That something is what Robin Hanson called the Great Filter. And the question that the Great Filter forces, the one that makes most people stop reading, is whether the filter is behind us or ahead of us. If it is behind us, then we are the rare survivors. The hard step is already in our past. The dangerous junction has been crossed. We are, improbably, on the far side of whatever it is that stops civilizations from becoming visible, and the road ahead, while not guaranteed, is open. If it is ahead of us, then civilizations commonly reach our level of technological development and then fail to persist. The filter operates not on microbes or eukaryotes or multicellular life, but on technological civilizations, on species that have built radio telescopes and nuclear weapons and artificial intelligence, on species exactly like us. In that case, the silence of the sky is not a mystery about the past. It is a warning about our future. And the evidence that tells us which of those two possibilities is more likely is the evidence about what is happening right now on this planet, in this decade, in this precise technological moment. That is why the final answer is so specific. That is why most researchers who know it will not say it plainly. And that is where this investigation is heading. But to get there, we need to go through the filter mechanism carefully, because understanding what it is and how it works is what transforms it from an abstract statistical concept into a statement about the next 100 years of human civilization. The investigation continues. The Great Filter does not announce itself. It does not arrive with warning signs or preliminary tremors that a civilization can read and respond to in time. That is precisely what makes it a filter rather than a challenge. Challenges can be met. Filters sort. They operate on populations, not on individuals, and they operate consistently enough across many independent histories that the outcome, a quiet galaxy, becomes statistically reliable. Whatever the filter is, it must be the kind of thing that hits civilization after civilization across wildly different planetary environments, different biologies, different cultural histories, and different starting conditions, and produces the same result with enough regularity to leave the sky looking as empty as it does. That consistency requirement is itself a clue, and it is worth staying with it before we examine the specific candidates. Think about what it would take to produce consistent results across civilizations that arose independently on different worlds, around different kinds of stars, with different biochemistries, different evolutionary histories, and different cultural trajectories. For a filter to work this reliably, it cannot be something that depends on specific cultural choices or specific historical accidents. It cannot be something that one civilization survives by luck and another fails at by carelessness, because if survival is a lottery, some civilizations win it, and the galaxy accumulates survivors over time. A reliable filter must be something that is either physically inevitable given certain conditions, or statistically so likely to end a civilization that the survivors are too rare to notice even across galactic scales. This is the argument's sharpest edge. The filter's consistency implies something deep and structural about what civilizations do when they reach a certain threshold of power, not what they might do in some unlucky configurations. What they reliably do, what the physics and the sociology and the technology of power at scale consistently produce. To appreciate that argument fully, we need to go through the candidate filters carefully, starting with the ones that locate the bottleneck in the past, before civilization develops technology, and moving to the ones that locate it in the present and future, after civilization has already reached our stage of development. The emotional temperature of the investigation will change as we move through this list, because the further forward in time the filter sits, the more directly it speaks to our own situation. The Great Filter framework begins with a list of steps and asks which one is nearly impossible. We already examined the biological candidates in the rare Earth chapter: abiogenesis, the emergence of eukaryotic cells, the rise of complex multicellularity, the development of technological intelligence. Each of these is a genuine candidate for a past filter, a step so improbable that most worlds never clear it. If any one of them is genuinely vanishingly rare, the galaxy can be empty without requiring that civilizations fail after they emerge. The emptiness would simply reflect the difficulty of getting started, but the rare Earth candidates face a numbers problem that grows sharper the more planetary data we collect. The exoplanet revolution has confirmed that the raw materials are common. Rocky planets in temperate orbits around stable stars are not rare exceptions. Chemistry is universal. The same organic molecules found in meteorites and interstellar clouds are the same molecules that underlie biochemistry on Earth. The building blocks are scattered everywhere, assembled by the same physics in countless environments. Every year of new astronomical data makes the case that the early steps, the ones that produce living planets from raw chemistry, are not obviously improbable. They may be common. They may be nearly inevitable given the right conditions. And if the early steps are easy, the filter must be later. This is the asymmetry that makes the great filter analysis so uncomfortable. Good news about biology is bad news about the future. Evidence that life arises readily is evidence that the filter is not in the distant past. And the further forward the filter sits, the closer it gets to us. Consider the specific evidence that pushes against a past filter. The timing of life on Earth is suggestive in a way that cuts against the idea that abiogenesis is nearly impossible. Life appears to have arisen on Earth within a few 100 million years of the planet's surface stabilizing enough to support it, which in geological terms is relatively quickly. The early Earth was hostile. The heavy bombardment period, lasting until roughly 3.8 billion years ago, subjected the surface to repeated sterilizing impacts. Yet life's chemical signatures appear in rocks dated to 3.7 to 3.8 billion years ago, and some disputed evidence pushes the traces back even further. If abiogenesis were a nearly impossible process, requiring extraordinarily long random search times, we would expect it to have taken much longer on Earth given how recently the planet became hospitable. The fact that it appears to have happened quickly suggests either that the conditions were particularly favorable here, or that the process is not as improbable as extreme rare Earth proponents require. Laboratory experiments on prebiotic chemistry reinforce this unease. Since Stanley Miller and Harold Urey's famous 1953 experiment demonstrating that amino acids could be synthesized from simple chemicals under conditions resembling early Earth's atmosphere, the field has advanced dramatically. We can now produce amino acids, nucleobases, lipid membranes, and RNA-like molecules under plausible prebiotic conditions in laboratory settings. The RNA world hypothesis, which proposes that RNA served as both genetic material and catalyst before the evolution of DNA and proteins, has accumulated substantial experimental support. The specific chemical steps from simple molecules to self-replicating polymers remain challenging and incompletely understood, but the gap has narrowed considerably compared to what it looked like in 1953. Abiogenesis is not a solved problem, but it looks increasingly like an engineering challenge rather than a miracle. The broader chemical context supports the same tentative conclusion. Complex organic molecules are found throughout the interstellar medium, in dense molecular clouds where new stars and planets are forming, in meteorites that have sampled the early solar system's chemistry, and in the atmosphere of Titan, Saturn's moon, where an extraordinarily rich organic chemistry operates without any biological assistance. The universe appears to be very good at making the building blocks of life without any biological guidance. Whether it is equally good at assembling those building blocks into the first self-replicating, metabolizing systems is the remaining question, and the answer is not yet in. But the trend of the evidence is toward chemistry being the easy part, not the hard part. If that is right, if life arises readily on habitable worlds, then the filter is not at abiogenesis. And the chain of steps between the first microbe and the first radio telescope becomes the place where the silence must be explained. Within that chain, the transition from simple microbial life to complex multicellular life is the biological candidate that retains the most force. The argument from timing is again relevant here, but it cuts in the opposite direction from the abiogenesis case. Life appeared quickly on Earth, but complex multicellular animals appeared only after roughly 3.5 billion years of single-cell dominance. That is a very long delay, and it is not obviously explained by external conditions waiting to become favorable, though the oxygen story is part of it. The persistence of the microbial world as the dominant life form for most of Earth's biological history is consistent with the idea that the transition to complex multicellularity is genuinely hard, perhaps much harder than abiogenesis, and perhaps the hardest step in the entire chain before intelligence. The endosymbiotic merger that produced the eukaryotic cell remains the most compelling single-event bottleneck in biological history. Everything complex, every plant, every animal, every fungus, every alga that builds elaborate structures is descended from that one merger event or from its descendants. It happened once in 4 billion years of life on Earth. The statistical interpretation of that frequency is uncertain, but once in 4 billion years is consistent with the event being very improbable, not just waiting for the right moment. If the eukaryotic merger is the filter, the implications are not catastrophic for us. It is behind us. We are on the far side of it. The galaxy can be empty because most biospheres are stuck at the prokaryotic stage indefinitely, never producing the energetically complex cells that enable large, metabolically demanding organisms. Under this interpretation, microbial life might be common across the universe, while complex life is extraordinarily rare, and we are an anomaly, a lucky product of an improbable chemistry event that happened to produce the preconditions for everything that followed. This would be the most comforting version of the Great Filter. It places the bottleneck far in our past, in a biological detail so specific and so dependent on the particular chemistry of two ancient cells that it has no direct implications for our technological future. We would be rare survivors of a biological lottery, not a civilizational one. The sky would be quiet because of ancient cell biology, not because of the fate of technological species. But comfort is not a reliable guide to truth. The question is not which filter location feels best. The question is which filter location is most consistent with all the available evidence, and the evidence does not strongly favor the comfortable option. Here is the diagnostic test that would distinguish a past filter from a future one, stated as plainly as possible. If the filter is in the past, the universe should show a pattern where planets are common, prebiotic chemistry is common, but life is rare, or life is common but complex life is rare, or complex life is common but intelligence is rare. The filter's location determines where in the chain the universe starts to look sparse. If we find abundant microbial life on Mars, on Europa, on Enceladus, the filter is not at abiogenesis. If we find abundant complex multicellular life on other worlds, the filter is not at complexity. Each positive finding about biology elsewhere pushes the filter forward in time and closer to the technological threshold. If the filter is in the future, the universe should show a pattern where biology is common, complexity is common, intelligence is common, but technological civilizations do not persist. The universe would be full of life, potentially full of minds, but devoid of the long-term, large-scale civilizations that would produce visible techno-signatures. The sky would be quiet not because minds are rare, but because minds with power reliably destroy themselves or are destroyed before they become prominent. We cannot yet perform this test with certainty, because we cannot yet directly survey biology on other worlds at the level of detail needed to distinguish these cases. But the direction of the evidence from our own solar system will be extraordinarily informative. Mars, once wet, may have hosted life. Europa almost certainly has a liquid ocean with chemical energy gradients. Enceladus is actively venting water from its ocean into space where we can analyze its composition. If any of these worlds host or once hosted even simple microbial life, that is evidence for biology being easy. And biology being easy is evidence for the filter being late. And the filter being late is the uncomfortable conclusion. This is why a discovery of life on Mars would be simultaneously the most exciting scientific result in history and one of the most distressing. Not because Mars life would be dangerous, but because Mars life would be informative. It would narrow the Great Filter's location. It would push the bottleneck out of the comfortable past and into the uncomfortable future. It would transform a puzzle about ancient cell biology into a question about technological civilizations, including the one that is currently building the spacecraft going to check. Carl Sagan understood this. He wrote about it. He said that if we go to Mars and find life there, even just microbes, even just fossils, we should not celebrate uncritically. We should feel the weight of what that discovery implies, because the silence of the sky combined with the commonality of life implies a very specific and very dark conclusion about what happens to civilizations that develop technology. Sagan said this before the Great Filter had been formally articulated by Hansen, but the logic was already clear to him. Now we move to the filter candidates that are not biological at all. The candidates that locate the bottleneck not in the emergence of life or intelligence, but in what intelligent civilizations do with the power they develop. These are the candidates that make researchers fall quiet. Not because they are scientifically disreputable, they are in fact the most rigorous and defensible candidates given the evidence, but because they are personally relevant in a way that no biological bottleneck can be. A filter located in ancient cell chemistry is a historical curiosity that has no bearing on our immediate future. A filter located in the behavior of technological civilizations is a description of a pattern that we may already be entering. The candidates in this category are not wild speculation. They are extrapolations from our own history and from basic physical constraints on what civilizations can do with power, and they are disturbingly consistent with what we observe when we look honestly at our own trajectory. The first and most straightforward candidate in this category is self-destruction through technology. The argument is simple. Civilizations develop technology because technology solves problems. Technology that solves problems at small scales tends to be extended to larger problems at larger scales, because the same mental faculty that enables tool use also enables the extension of tools to new domains. But technology that operates at larger scales also has larger failure modes, and failure modes that are large enough and fast enough and comprehensive enough can terminate a civilization before it has time to develop the wisdom or the institutional structures to manage them. The specific technologies that have this character are not hard to identify. We have been living with two of them for most of the second half of the 20th century. Nuclear weapons are the most obvious. We developed the ability to construct devices that could, if deployed at scale, end industrial civilization and possibly terminate our species within a few decades of the technology's invention. We came very close to using them during the Cuban Missile Crisis in 1962. The resolution of that crisis was partly rational and partly a matter of luck, of specific individuals making specific decisions at specific moments that could easily have gone differently. The world did not survive the Cold War because civilization was wise. It survived because certain human beings, in certain rooms, at certain moments, made choices that were not inevitable. That is not a robust safety mechanism for a species that will face such crises repeatedly across centuries and millennia. Biological weapons are a second candidate in the same category, technologies that can be weaponized to cause harm at scales that were impossible before the relevant knowledge was developed. The pathogen design space is vast, and as our understanding of genetics and synthetic biology improves, the capability to engineer dangerous organisms becomes more accessible, and the knowledge required to do so becomes less specialized. Unlike nuclear weapons, which require industrial-scale infrastructure that is difficult to conceal, a sufficiently advanced biological agent might be created by a small group with modest resources and released in ways that spread globally before the source is identified or the spread can be controlled. These are not hypothetical future concerns. They are technologies that exist now, that have been deployed in limited ways or nearly deployed in catastrophic ways, and that will remain permanently available to any civilization that crosses the threshold of understanding the relevant science. Once nuclear physics is known, it is known. Once synthetic biology is understood, it is understood. The knowledge cannot be uninvented, and the capability it enables scales with the technology rather than with the wisdom of the civilization deploying it. A third candidate is climate destabilization through industrial activity, which differs from the first two in that it is not a weapon and does not require malicious intent. It is simply a consequence of energy use at scale in an atmosphere that is sensitive to the composition of certain gases. The evidence that Earth's climate is being systematically altered by the accumulated emissions of industrial civilization is no longer scientifically disputed at the level of the basic mechanism. What remains genuinely uncertain is the full range of feedbacks, their timescales, and the extent to which human civilization can adapt to or mitigate the changes already set in motion. But the possibility that industrial civilizations, by their very nature, alter their home planet's climate in ways that eventually threaten the stability of the systems on which they depend is not a fringe concern. It is a mainstream scientific observation about the specific civilization we are inside. None of these three technologies is guaranteed to destroy our civilization. Humans have managed nuclear weapons for 7 decades without using them in war after 1945, though not without significant close calls. We have developed frameworks for biosafety and biosecurity even as the underlying knowledge has spread. We are now belatedly mobilizing to address climate change with a degree of seriousness that was absent a generation ago. The record is mixed and the trajectory is uncertain. But the great filter analysis does not ask whether a civilization can survive its technological adolescence. It asks whether most civilizations do. The distinction is crucial. If survival through this period requires an unusual combination of luck, wisdom, institutional quality, and cultural evolution that only a small fraction of civilizations possess, then the filter operates reliably enough to explain the silence, even if some civilizations do make it through. The ones that make it through are rare enough that the galaxy remains effectively empty of their signatures, or they are recent enough that their signatures have not yet had time to reach us. The filter does not need to kill every civilization. It only needs to kill enough of them, reliably enough, that long-lived, technologically prominent civilizations are too rare to appear in our surveys. A civilization's survival rate of 1 in 1,000 through the technological threshold period, combined with the underlying rarity implied by the other filters we have already examined, can produce a galaxy that looks as quiet as ours does. The arithmetic is not fussy about the specific mechanism. It cares only about outcomes. The possibility that civilizations destroy themselves is uncomfortable but familiar. We have been thinking about it since at least the 1940s, when the first nuclear weapons demonstrated that industrial civilization had the capability to terminate itself. What is less often appreciated is how the Great Filter framework transforms this concern from a general worry about human potential for self-destruction into a specific statistical claim about the universe. The statistical claim is this: if civilizations commonly destroy themselves at the technological threshold, then the paradox is resolved. The math works out. The sky is quiet because civilizations reliably pass through a period during which their technology outruns their wisdom, and the outcome of that period, when it goes badly, is fast enough and comprehensive enough to prevent recovery. The civilization collapses before it has time to expand beyond its home system, before it has time to develop the kind of distributed, redundant presence that would make it resilient to local catastrophe, and before it has time to leave the kind of durable thermodynamic fingerprints that would show up in our surveys. Notice what this implies. It implies that the civilizations we do not see are not simply failing to signal. They are ceasing to exist. The silence is not a communication choice. It is a cemetery, and it implies something about the timing. If civilizations regularly destroy themselves in the technological adolescence period, the period during which they develop the capacity for large-scale self-harm before they develop the wisdom or institutional structures to prevent it, then the filter is not located at some random point in the history of civilization. It is located at a specific technological level, a predictable stage. The stage at which a civilization has built the tools of mass destruction and global environmental manipulation, but has not yet built the social and political architecture to manage them reliably over centuries and millennia. What does that stage look like from the inside? It looks like a civilization that has nuclear weapons and is arguing about whether to use them. It looks like a civilization that has mapped the human genome and is beginning to synthesize pathogens. It looks like a civilization that is changing its own planet's atmospheric chemistry faster than its political systems can organize a response. It looks like a civilization that is developing artificial intelligence at a pace faster than it can understand the systems it is building or govern the deployment of those systems responsibly. It looks, in other words, recognizably like the civilization we are living in. The artificial intelligence filter deserves particular attention because it is the newest of the serious candidates and because it operates on a different timescale than the nuclear or biological threats. Nuclear weapons have been managed imperfectly for 7 decades through a combination of deterrence, arms control treaties, and institutional safeguards. Biological weapons have been managed also imperfectly through the Biological Weapons Convention and through the practical difficulty of deploying engineered pathogens reliably. Both of these threats are, to a significant degree, static. The technology has not changed as rapidly as it did in the early decades, and the relevant knowledge is at least partially bottled up in institutional and infrastructural constraints that slow its spread. Artificial intelligence does not share these characteristics. It is developing rapidly. The relevant research is largely public and widely distributed. The computational resources required to run advanced AI systems are becoming less specialized and more accessible, and the trajectory of improvement shows no obvious signs of plateauing at a level below the threshold of concern. The economic incentives driving AI development are enormous and globally distributed, meaning that slowing or coordinating development faces collective action problems that arms control regimes for nuclear weapons partially solved, but that AI governance has barely begun to address. The specific risk from artificial intelligence that is most relevant to the Great Filter analysis is not the science fiction scenario of a robot uprising. It is the more mundane but equally serious risk of misalignment. the development of AI systems that are extremely capable at pursuing specified objectives, but that pursue those objectives in ways that are indifferent or actively harmful to human values and human survival. An AI system that is optimizing a defined objective function without adequate constraints on how it pursues that objective can cause catastrophic harm, not because it has human-like malicious intent, but because it has no human-like values at all. It is simply pursuing its objective, and the pursuit turns out to be incompatible with the conditions that human civilization requires to persist. The technical challenge of ensuring that AI systems remain aligned with human values as they become more capable is called the alignment problem, and it is one of the most actively researched areas in AI safety. The challenge is not that alignment is obviously impossible. It is that it is not obviously solved, that the field is developing much faster than the safety research, and that the deployment decisions are driven by competitive pressures that reward capability over safety. These are familiar dynamics from other technological fields, including nuclear weapons and industrial chemistry, where the deployment pace consistently outran the governance capacity. What is different about AI is the potential speed of the capability jump. Systems that are inadequately controlled and extremely capable can cause harm on timescales too fast for human institutional response. None of this is certain. AI development might proceed in ways that remain manageable. The alignment problem might be solved before systems become dangerously capable. Governance frameworks might develop quickly enough to prevent the worst outcomes. These are all possible. But the great filter analysis does not ask what is possible, it asks what is typical. And the pattern we observe in our own history suggests that civilizations routinely deploy powerful technologies before they have adequate frameworks for managing the risks, and that the consequences of this habit have generally been managed by luck and by the relative slowness of the technologies involved rather than by foresight or institutional wisdom. If the pace of AI development outstrips the pace of governance development by a sufficient margin, and if the resulting systems cause sufficient harm before adequate controls are in place, the outcome could be a civilization that is permanently set back or ended by technology it developed and deployed without understanding. The filter would then be located precisely at the technological threshold we are currently crossing, the development of machine intelligence that exceeds human capability in strategically relevant domains before humanity has established the institutional architecture to manage what it has built. There is a version of the technological self-destruction argument that is not about weapons or about alignment failures. It is about resources and about the physical constraints that any civilization faces as it scales its energy use on a finite planet. Industrial civilization runs on energy. Energy use has grown continuously since the Industrial Revolution, driving improvements in living standards, medical care, transportation, communication, and virtually every other dimension of human welfare. The growth of energy use has been accompanied by the growth of a specific kind of byproduct, waste, in the form of heat, gases, particulates, and altered chemical cycles. At the scale of a single industrial nation, these byproducts can be managed, displaced, or absorbed by natural systems faster than they accumulate. At the scale of a planetary civilization consuming energy at the rate of a significant fraction of the total solar input, the byproducts become a geological force in their own right. This is not a speculative concern about the distant future. It is a measured reality about the present. Atmospheric carbon dioxide concentrations are higher than at any point in at least 800,000 years of geological record, probably much longer, and rising faster than at any point in the same record. The rate of species extinction is running at a pace estimated to be hundreds to thousands of times higher than the background extinction rate that characterized the history of life before industrial civilization. Ocean chemistry is changing faster than at any time since at least the last mass extinction event. The biosphere is being reshaped at a pace that geological time resolution cannot even meaningfully capture because the change is happening within a single century. Whether these changes will terminate our civilization is not certain. Human adaptability is real, and civilization has survived major disruptions before, but the great filter question is not whether our civilization will certainly collapse. It is whether civilizations at this stage of development typically manage the transition to a stable, long-term relationship with their home planet's physical systems, or whether they typically overshoot the planet's capacity and suffer consequences that prevent them from reaching the durable, spacefaring, galaxy-influencing scale that would make them detectable. The evidence from our own solar system is relevant here in a sobering way. Venus is often cited as a cautionary tale, though the parallel is imperfect. Venus is Earth-sized, formed at roughly the same time from similar materials, and sits at a distance from the Sun that might in principle have allowed liquid water early in its history. Yet Venus today has a surface temperature of over 460 degrees Celsius, an atmosphere 90 times denser than Earth's, consisting primarily of carbon dioxide, and no signs of life. Whether Venus ever had liquid water and lost it due to a runaway greenhouse effect driven by its proximity to the Sun, or whether it never had favorable conditions, is still debated. But the physical mechanism that could transform a temperate, wet planet into a pressure-cooked desert is well understood, and it involves carbon dioxide, water vapor, and a positive feedback between warming and increased atmospheric water content that is essentially irreversible once triggered. The physical possibility of a civilization triggering something analogous by altering its own planet's atmospheric composition faster than natural feedbacks can compensate is not zero, though the timeline and the specific triggering conditions are uncertain. Mars tells a different story that is in some ways equally instructive. Mars once had a much denser atmosphere, liquid water on its surface, and possibly conditions favorable to life. It lost its atmosphere over billions of years through a combination of low gravity making atmospheric escape easier, and the loss of its magnetic dynamo making the remaining atmosphere vulnerable to solar wind stripping. Mars did not have a civilization to accelerate this process, but the outcome, a thin-atmosphered, cold, radiation-bathed desert, illustrates what happens to a planet's surface conditions when the parameters that maintain habitability shift in the wrong direction. For a civilization on such a world, even a modest acceleration of atmospheric loss through industrial activity could produce consequences that far outstripped any protective response. Neither of these analogies is precise. Earth is not Venus and is not Mars, and our specific situation has its own distinctive parameters, but they illustrate that planetary habitability is not a given across infinite timescales. It is a maintained condition, dependent on a balance of feedbacks that can be shifted. A civilization that shifts those feedbacks faster than it can adapt to or reverse the shift faces a genuine survival problem, and the survival problem is self-generated by the very industrial processes that gave the civilization its power. The resource depletion and ecological collapse argument extends the same logic to biological systems, which are more immediately relevant to our current situation than atmospheric chemistry. Industrial civilization depends on a stable biosphere not just for food, but for the regulation of air, water, soil chemistry, and climate. Natural ecosystems perform services that would be extremely expensive or impossible to replicate through technology at the scale required to support billions of humans. Pollination, water purification, carbon sequestration, soil formation, and the regulation of atmospheric chemistry are all performed by living systems that evolved over millions of years, and that depend on biodiversity and ecosystem integrity to function. When those systems are disrupted faster than they can recover, the services they provide degrade. When they collapse, the services they provide stop. We are currently experiencing the fastest mass extinction event in the history of complex animal life, driven primarily by habitat destruction, pollution, invasive species introduction, overexploitation, and climate change, all of which are consequences of industrial activity at global scale. The trajectory is not toward stabilization. It is toward continued acceleration, driven by population growth and by the expanding economic aspirations of billions of people in developing countries who have legitimate claims to the standard of living that industrial civilization can provide. There is no obvious mechanism by which this trajectory reverses before the consequences become much more severe than they currently are. Again, this does not guarantee civilizational collapse. Human ingenuity and adaptability are real, and the history of environmental concern in wealthy countries shows that political systems can, under sufficient pressure, implement protections that reduce the pace of ecological damage. But the Great Filter analysis does not ask what one civilization can do under favorable circumstances. It asks what technological civilizations typically do across a wide range of planetary environments, cultural contexts, and institutional capacities. And the answer that the evidence suggests is that they typically exhaust and disrupt the natural systems on which they depend faster than those systems can recover, at least during the period before the civilization develops either the technology to decouple its needs from biological systems entirely or the governance capacity to manage its impact at global scale. The technological decoupling option is real but uncertain in its timeline. Synthetic biology, advanced materials science, and artificial photosynthesis could in principle reduce civilizations' dependence on natural ecosystem services. Vertical farming, lab-grown proteins, and water recycling technologies could reduce the land area and water demand required to feed a large population. Energy systems that do not depend on burning stored carbon could reduce atmospheric alteration to manageable levels. These technologies exist in various stages of development. Whether they can be deployed at sufficient scale and with sufficient speed to prevent catastrophic ecosystem collapse before the natural systems have been too severely damaged is an open question, and an urgent one. The governance capacity option is also real but deeply uncertain. Managing the global commons, whether it is the atmosphere, the ocean, the biosphere, or increasingly the electromagnetic spectrum and near-Earth orbital space, requires coordination mechanisms that work across sovereign nations with different interests, different time horizons, and different capacities. The history of international environmental governance is mixed at best. The Montreal Protocol's success in addressing ozone depletion demonstrates that global coordination is possible, but it required a relatively simple problem with a relatively small number of key actors and a scientific consensus that emerged before the damage was irreversible. Climate change has proven much harder to coordinate around, despite decades of scientific consensus and increasingly obvious consequences, because the affected industries and the required sacrifices are larger and more politically sensitive. Whether global governance mechanisms will develop fast enough to prevent the worst outcomes from climate change, biodiversity loss, and other planetary-scale challenges remains genuinely uncertain. The Great Filter hypothesis says that, across many independent trials in many different planetary civilizations, the answer is typically no, not fast enough, not reliably enough, not consistently enough to allow civilizations to pass through the threshold and emerge with their industrial base and their biosphere intact. We are now at the part of the investigation where the Great Filter stops being an abstract concept and starts being a statement about the probability distribution of our own future. The filter framework says the sky is quiet because civilizations reliably fail at a predictable state. The evidence we have examined suggests that the most probable location for that filter is not in the distant past, not in ancient cell biology, not in the difficulty of complex multicellularity, but in the period during which a civilization develops the capacity for self-destruction and must develop the wisdom and governance capacity to manage it before it is too late. We are in that period. This is not a metaphor or a philosophical observation. It is a statement about where we are on the timeline of the filter, if the filter is real, and if it is located where the evidence suggests. We have nuclear weapons, and we have not yet established the global governance architecture that would make their elimination permanent and verifiable. We are developing artificial intelligence at a pace that our safety research and our governance frameworks are not keeping up with. We are altering our planet's chemistry and biology faster than our political systems are organizing an adequate response. We are, by every observable measure, in the exact zone that the Great Filter analysis identifies as the danger period. That is why most researchers who have worked through this analysis carefully do not say it out loud. Not because it is scientifically disreputable. It is, in fact, the most scientifically defensible conclusion given the evidence. It is because the conclusion is personal. It is because saying it plainly means saying that the silence of the sky is not a mystery about alien biology. It is a warning about what typically happens to civilizations like us during periods like this. The warning does not mean the outcome is determined. It means the risk is real, the risk is systematic, and the risk is at a level that should command the same priority as any other existential threat, which is to say the highest priority a civilization can assign. If the filter is real and if it is ahead of us, the most important question in the world is whether we are going to be the exception or whether we are going to contribute another data point to the silence. Before we close out the self-destruction hypotheses, we should examine the specific claim about timescales more carefully, because the timescale argument is where the filter analysis becomes most precise and most disturbing. The core claim is that technological civilizations spend only a relatively brief window of time in the danger zone, the period between developing the capacity for self-inflicted civilizational harm and either surviving through wisdom and governance development or not surviving. If civilizations that survive this window go on to become long-lived, spacefaring, physically prominent presences in the galaxy, then the sky's silence implies that most civilizations do not survive the window. The window must be short relative to the lifetime of a surviving civilization, and the probability of surviving must be low. Otherwise, there would be enough survivors to make the galaxy detectably occupied. Putting numbers on this is necessarily speculative, but the exercise is instructive. If the average window of danger lasts a few centuries, from the development of industrial-scale weapons of mass destruction to either civilizational collapse or successful long-term governance of those weapons. And if the probability of surviving the window is, say, a few percent, then the fraction of civilizations that become long-lived and prominent is very small. Multiplied across the Drake equation's other terms, even modest estimates for the difficulty of earlier steps, the expected count of currently observable civilizations could easily be consistent with zero detections in our surveys. The numbers are not precise. The window could be longer or shorter. The survival probability could be higher or lower, but the directional logic is robust. If the danger period is real, and if survival requires a combination of institutional wisdom, cultural maturity, and political coordination that is genuinely difficult to achieve, then the filter operates reliably enough to explain the silence without invoking extraordinary rarity of life or intelligence. What makes this calculation particularly unsettling is that it is self-referential. We are inside the window. We are generating the very data point whose outcome will contribute to the statistic. The civilizations that did not survive their windows are part of the distribution that the filter analysis describes. We are currently in the process of determining whether we join the survivors or the non-survivors, and the filter analysis says that the non-survivors dominate the distribution. This is the conclusion that most people stop reading before they reach, not because it is scientifically unsound. It is the most defensible conclusion, because it means that the Fermi paradox is not a puzzle about astronomy. It is a warning about us. Not every hypothesis that explains the silence relies on self-destruction. There is a family of explanations that locate the problem not in what civilizations do to themselves, but in what external forces do to civilizations, or in what civilizations do to each other. The Berserker hypothesis, first articulated by Fred Saberhagen in fiction and later developed as a serious scientific hypothesis, proposes that the galaxy has been seeded with self-replicating probes programmed to destroy any civilization they detect above a certain technological threshold. The motivation for building such probes could vary. An ancient civilization might have determined that the proliferation of technological species was an existential threat to their own survival, and the most effective solution was to build automated systems that would prevent any other species from reaching a level of capability that could challenge them. Once built, such probes could operate indefinitely without further direction, replicating and spreading through the galaxy while monitoring for the kinds of electromagnetic and thermal signatures that mark technological development. The Berserker hypothesis has a certain internal logic. It does not require that the galaxy be actively managed by a currently existing civilization. It only requires that some civilization, at some point in the galaxy's past, built the probes and set them running. The probes then operate autonomously, explaining the silence without requiring the presence of their builders. The galaxy would be quiet because any civilization that became loud enough to notice would be targeted and eliminated before it could spread. The problem with the Berserker hypothesis, as a complete explanation for the paradox, is that it predicts specific observable consequences that we do not see. If probes are systematically targeting and eliminating civilizations, their activity should produce detectable signatures, unusual energy releases, anomalous dimming events in stellar systems, or patterns of destruction that stand out against the background. The galaxy should contain the ruins of civilizations that were targeted, ruins that might be detectable as systems with unusual chemical compositions or unusual infrared signatures. We see none of this. The Berserker hypothesis also raises questions about why our civilization has not been targeted yet, given that we have been producing radio leakage for a century and operating high-powered radar systems that are detectable at significant distances. If the probes are monitoring for exactly this kind of electromagnetic signature, we should have been identified and targeted by now, or at least should be experiencing the approach of something headed our way at a fraction of light speed. The absence of obvious targeting is either because the probes do not exist, or because they operate on timescales that exceed our current experience, or because we are too small and too recent to have triggered the threshold yet. None of these are satisfying resolutions to the paradox, though the last one is particularly chilling if true. The dark forest hypothesis, most prominently associated with Chinese science fiction author Liu Cixin, but independently developed by other thinkers, proposes that the silence is a stable strategy rather than an outcome of destruction. The hypothesis begins with two axioms. First, that all civilizations prioritize survival above all other values. Second, that resources in the universe are finite and that civilizations are fundamentally in competition for those resources. From these two axioms, it argues that any civilization that detects another civilization faces a decision about whether to communicate or destroy, and that the optimal strategy, given uncertainty about the other civilization's intentions and capabilities, is always to destroy before being destroyed. The logic is game theoretic. If you detect another civilization, you cannot know whether it is friendly or hostile. If it is hostile and you communicate, it now knows your location and may destroy you. If it is hostile and you do not communicate, you may be able to destroy it before it destroys you, removing a potential future threat. If it is friendly and you destroy it anyway, you lose a potential ally but gain security. If it is friendly and you communicate, you gain an ally but also expose yourself. Under sufficiently extreme assumptions about the cost of being destroyed and the difficulty of verifying intentions, the dominant strategy is always to destroy first and ask questions never. Any civilization that follows this logic will destroy any other civilization it detects, and any civilization that is regularly broadcasting its presence will be regularly hunted. The stable outcome of a galaxy full of civilizations following this logic is universal silence. Every civilization hides because broadcasting is lethal. Every civilization destroys any signal it detects because detected signals are threats. The galaxy is a dark forest where every civilization moves quietly through the shadows and shoots anything that makes noise. The dark forest hypothesis has a certain bleak elegance. It explains why the sky is quiet, why we see no megastructures and no signals, and why any civilization with a long enough history to understand the game would never transmit a beacon that could be detected. It also has a particular relevance to our own situation. If the hypothesis is correct, then SETI is not just futile but dangerous, because searching for signals and potentially responding to them is exactly the behavior that gets civilizations targeted. The hypothesis has serious weaknesses, however, and examining them is important because the weaknesses tell us something about what kind of explanation actually fits the evidence. First, the dark forest logic requires that all civilizations reach the same conclusion about the optimal strategy, and that they maintain that strategy reliably across all members of the civilization forever. A single rogue actor, a single idealistic scientist, a single religious group that believes in cosmic brotherhood could transmit a signal that betrays the civilization's location. Maintaining total communication silence across an entire civilization, across all its internal factions and all its historical eras, is an extraordinarily demanding coordination requirement. On Earth, we already transmit prolifically and have been doing so for a century, suggesting that the coordination requirement may be too demanding for at least some civilizations to meet. Second, the dark forest hypothesis predicts that the galaxy should contain evidence of systematic destruction, the ruins of civilizations that were detected and eliminated. Targeted star systems should show unusual properties, unexpected chemical compositions, anomalous energy releases, or statistical deviations from expected stellar populations in regions that should have hosted long-lived civilizations. We do not see this, or at least we have not yet identified it. The galaxy's stellar populations look consistent with natural evolution rather than systematic culling. Third, the hypothesis rests on the assumption that resources are so scarce that civilizations are inevitably in competition for them. But in a universe with hundreds of billions of stars, each with abundant energy and material, the resource competition argument is hard to sustain unless civilizations are so common and so energy-hungry that they actually exhaust the galaxy's accessible resources. In a galaxy with even hundreds of civilizations, each occupying one stellar system, the competition for resources is not obviously so intense as to make predation the dominant strategy. Cooperation and coexistence are not obviously inferior strategies in a universe with this much room and this much energy. The dark forest hypothesis is therefore a possible explanation for the silence, but it is not a particularly well-supported one when examined carefully. It requires strong assumptions that may not hold, predicts observational consequences we do not see, and may underestimate the diversity of strategy that real civilizations would adopt across their histories. The simulation hypothesis offers a completely different kind of explanation, one that operates at a level above the physics of the galaxy rather than within it. The core argument, developed most influentially by philosopher Nick Bostrom, begins with the observation that sufficiently advanced computing technology should be able to run simulations of physical systems at extraordinary levels of detail, including simulations of conscious minds. If this is possible, and if civilizations regularly develop this technology and choose to run large numbers of such simulations, then the number of simulated minds in the universe could vastly exceed the number of biological minds. Given that we have no obvious way to distinguish whether our own minds are biological or simulated, the probability that any given mind is in a simulation rather than in base reality could be very high, simply by the numbers. Applied to the Fermi paradox, the simulation argument suggests that the silence is a feature of the simulation rather than a fact about base reality. The simulator has chosen to present us with a cosmos that appears devoid of other intelligent life, either because the simulation is specifically focused on our civilization, or because running a fully populated galaxy at full resolution would be computationally expensive, and the simulator has opted not to do so, or because the silence is part of the scenario being explored. Under this hypothesis, the Fermi paradox is not a puzzle about astronomy. It is a puzzle about what kind of simulation we are inside, and why the programmers chose to set the parameters this way. The simulation hypothesis is genuinely unfalsifiable in its strong form, which is both its appeal and its weakness. If the apparent emptiness of the cosmos is a deliberate choice by a simulator, there is no observation we could make that would contradict that explanation, because the simulator can always have constructed the observations we see. An explanation that cannot be contradicted by any possible evidence is not a scientific explanation in the standard sense. It is a framework for reinterpreting evidence rather than a hypothesis that the evidence can test. This does not make the simulation hypothesis incoherent or irrational. It is a logically consistent set of claims. But as a solution to the Fermi paradox, it is deeply unsatisfying precisely because it refuses to play by the rules of the investigation. We are looking for explanations that make testable predictions and that can be compared against each other on the basis of evidence. The simulation hypothesis says that all the evidence is constructed by an external agent whose motivations and methods we cannot access, which makes it immune to evaluation by the methods we are using. The simulation hypothesis is perhaps best understood not as an answer to the Fermi paradox, but as a meta-level dissolution of the question itself. It says the question is misconceived because the universe we are analyzing is not what it appears to be. That is a possible response to a hard problem, but it is the kind of response that closes doors rather than opening them, and investigations are better served by open doors. We are left, then, with the landscape of remaining serious candidates after working through the full range of proposed solutions. The "we have not searched enough" explanation is partial and important but insufficient. The physical distance and communication difficulty arguments are real constraints that modify expectations but do not dissolve the paradox. The timing arguments, that we are simply too early, dissolve under pressure from galactic timescales. The rare Earth hypothesis is a genuine possibility that may be partially correct, but struggles with the numbers required to fully explain the silence. The Berserker hypothesis and the dark forest hypothesis face observational challenges and internal logical requirements that are hard to satisfy. The simulation hypothesis is unfalsifiable and therefore outside the investigation's proper scope. What remains after honest evaluation is a combination of two explanations that reinforce each other and that together are genuinely consistent with all the evidence. The first is that complex intelligent life is somewhat, though not extraordinarily, rare. Not as rare as extreme rare Earth requires, but not as common as naive optimism predicts. The specific bottleneck may be in biological transitions, in the emergence of cumulative culture, or in the specific conjunction of conditions that produces tool-using intelligence rather than the many alternative forms that evolution can produce. This portion of the explanation reduces the expected count of technological civilizations without eliminating it. The second and more powerful is that technological civilizations are fragile at the threshold of self-destruction and typically fail to navigate it successfully. The filter is not ancient, it is present. It operates on civilizations that have already cleared all the biological hurdles and reached the stage of industrial technology, and it hits them during a specific period when their capabilities outrun their wisdom and their governance. The failure modes are various, but all have the same character. Technology enables harm at a scale that the civilization's social architecture cannot manage, and the result is collapse before the civilization becomes durable enough to resist it. Together, these two explanations produce a universe that looks like the one we observe. Biology is somewhat rare, which reduces the initial count. Civilizations are fragile at the threshold, which reduces the fraction that survive to become prominent. The product of these two effects is a galaxy that is essentially empty of durable, detectable civilizations, which is what we see. The specific, unwanted implication of this combination is that the silence is not a statement about alien biology. It is a statistical description of what civilizations do when they develop the power to destroy themselves and lack the institutional capacity to prevent that destruction. It is a description that our civilization is currently living, in real time, in the decisions being made right now about nuclear weapons governance, artificial intelligence development, climate policy, and biosecurity. There is a line of reasoning that connects the silence of the sky to the urgency of our current moment, and it is worth following carefully because it is the conclusion toward which this entire investigation has been building. If the Great Filter is ahead of us, and if it operates during the period of technological adolescence, then the probability that we survive the filter is not determined by our biology or our evolutionary history. It is determined by what we do in the next few centuries. The filter's location is not a verdict, it is an observation about typical outcomes. And typical outcomes can be altered by atypical behavior, by civilizations that take the filter seriously, that treat the silence as a warning rather than a mystery, and that organize their resources and their attention around the problem of surviving their own power. The question of whether this civilization can alter its trajectory is not an astronomical question. It is a political, social, technical, and philosophical question, one that involves governance structures, cultural values, technological design choices, and the distribution of power and knowledge across 7 billion people. But the astronomical evidence is relevant to it, because the astronomical evidence provides the context in which the question arises. We did not develop nuclear weapons in a vacuum. We developed them because physics was understood and because competitive pressures between states created incentives for deploying the most powerful available tools regardless of long-term consequences. We did not begin altering the atmosphere out of malice. We did it because industrial processes released energy cheaply, and the consequences were not immediately apparent to those making the decisions. We are not developing AI without forethought. But the forethought that exists is unevenly distributed, poorly funded compared to the development it is trying to monitor, and structurally disadvantaged by competitive dynamics that reward deployment speed over safety verification. These are patterns. They are recognizable patterns that recur across technological developments and across political systems and across cultural contexts. They are the kind of patterns that, if they recur reliably enough across many civilizations, would produce the silence we observe, not through malice or extraordinary bad luck, but through the ordinary operation of competitive dynamics and short-term incentives in the presence of technologies that can cause catastrophic long-term harm. The Fermi paradox in its deepest form is not asking where the aliens are. It is asking why intelligent civilizations do not become durable. And the most defensible answer, the one that survives contact with the evidence, is that they typically fail to develop the institutional wisdom to manage their own power before that power is deployed in ways that prevent recovery. We are inside the process that the paradox is describing. The silence is the outcome of that process for civilizations that do not navigate it successfully. Whether we join the silence or the exceptions depends on decisions being made right now, in this decade, in this generation, by people who are for the most part not thinking about the Fermi paradox when they make those decisions. The investigation has one more territory to cover before it closes, the specific technosignatures that next-generation telescopes might detect, and what those detections or continued non-detections will tell us about where the filter sits. JWST has already begun the process of reading planetary atmospheres at a level of detail that was not possible before. The data are thin and the interpretation is difficult, and the specific claims about individual planets have already proven contentious in the ways that early results in a new field always are. But the direction of the inquiry is correct, and the capability will only improve. The biosignature search is not primarily about detecting radio signals. It is about detecting chemical imbalances that nature alone struggles to maintain. Oxygen in the presence of methane is the canonical example. These two gases react with each other and destroy each other over relatively short timescales, so their simultaneous presence in significant quantities requires a continuous source of both, which on Earth is provided by biological activity. An oxygen-methane disequilibrium in a planetary atmosphere is a candidate biosignature, though not an unambiguous one, because abiotic processes can sometimes produce similar-looking chemistry under the right conditions. The broader search for biosignatures involves looking for phosphine, dimethyl sulfide, nitrous oxide, and various other molecules that are associated with biology on Earth, and that would require unusual chemistry to produce abiotically. The search involves looking for the overall chemical context of a planetary atmosphere, not just individual molecules, because the combination of gases and the relationship between their abundances can be more informative than any single compound. an atmosphere that contains many biological gases simultaneously, in proportions consistent with a living biosphere, is a stronger candidate than an atmosphere with one unusual molecule that might have an abiotic explanation. The James Webb Space Telescope is probing the atmospheres of planets around cool M-dwarf stars most effectively, because those planets transit their host stars more frequently and more deeply, providing more light passing through the atmosphere for spectroscopic analysis. The results so far are a mix of confirmed atmospheric detections and challenging non-detections, with interpretation complicated by clouds, hazes, stellar contamination, and the inherent difficulty of measuring a thin ring of gas from across dozens of light years. The field is progressing rapidly, and within the next decade, we should have substantially better constraints on the chemistry of many nearby exoplanet atmospheres. What would the discovery of a biosignature tell us about the Fermi paradox? The answer depends on where in the biological chain the biosignature sits. A simple chemical disequilibrium, consistent with microbial metabolism, would suggest biology is common, which, as we have discussed, would push the filter forward in time. Complex and unambiguous biosignature, consistent with a globally productive, multi-component biosphere, would push it further forward. Detection of a technosignature, an atmospheric composition that requires deliberate industrial activity rather than biology, would be the most consequential possible finding and would essentially prove that the filter is in our future. The absence of technosignatures in continued and improving searches would itself be informative. As our instruments improve and our survey coverage expands, the non-detection of obvious infrared signatures from stellar-scale engineering becomes an increasingly strong constraint. If the next generation of space infrared telescopes surveys thousands of sun-like stars at higher sensitivity and still finds no anomalous sources that survive scrutiny, the constraint on the frequency of long-lived, energy-intensive civilizations becomes significantly tighter. The silence would be measured more precisely, which would narrow the range of filter hypotheses that fit it. The Breakthrough Listen program, the most well-funded SETI initiative in history, is conducting radio and optical searches at sensitivity levels and coverage fractions that exceed all previous efforts combined. Its non-detections over the next decade and 2 decades will contribute meaningfully to the constraint, even if they cannot be definitive. Each passing year of silence at higher sensitivity is a more precise measurement of the absence, and more precise measurements are more informative about the nature of what is absent. The picture that emerges from all of these converging lines of evidence is not one of sudden resolution. The Fermi paradox will not be solved by a single discovery, except possibly the discovery of a genuine technosignature, which would be transformative in a way that nothing else could match. Instead, the investigation will proceed incrementally, with each new result narrowing the space of viable hypotheses and forcing adjustments in which explanations remain plausible. The direction of that narrowing is clear. Every year of improving exoplanet data that shows rocky planets are common in temperate orbits removes another layer of the planetary rarity explanation. Every year of prebiotic chemistry research that shows organic complexity arises readily under plausible conditions removes another layer of the abiogenesis explanation. Every confirmed detection of atmospheric chemistry on an exoplanet that shows biology-like disequilibria pushes the filter further forward in time. And every continued non-detection of technosignatures at improving sensitivity constrains the frequency and longevity of civilizations more tightly. The investigation is converging, slowly and unevenly, toward the place where it has been pointing all along. Return now to the original question, the one Enrico Fermi asked over lunch in 1950, phrased not as a casual observation, but as the hard physical question it turned out to be: where is everybody? The answer that survives the investigation, that is consistent with the evidence across all its forms, that does not require special pleading or unfalsifiable assumptions, and that fits both the silence of the sky and the physical understanding we have built over 6 decades of searching, is this. They are not here because they did not last, not because they never arose, not because the universe is fundamentally hostile to intelligence or to biology, not because space is too big or signals too weak or timing too misaligned. They did not last because technological civilizations face a specific, predictable, severe challenge during the period when their power exceeds their wisdom, and most of them do not navigate it successfully. The silence is the record of that failure, accumulated across billions of years and hundreds of billions of stars, written in the absence of the technosignatures that should be everywhere if civilizations routinely survive their own power. We are inside the challenge right now. The filter is not behind us, and it is not in front of us in the sense of being distant. It is here, It is the decisions being made in the next century about the technologies we have already built and the technologies we are currently building. It is the question of whether this civilization, which has already cleared all the biological hurdles and reached the threshold of real civilizational power, will also develop the institutional wisdom, the political coordination, and the cultural maturity to manage what it has built before what it has built manages us. The silence of the sky is not a comfort. It is the most important piece of evidence we have about our own future. And the most important thing about evidence is that it can be acted upon. The cosmos is quiet. The question is whether we are going to be the reason or the exception. The investigation has established its central conclusion, but a conclusion without architecture is just an assertion. The work that remains is to build the full structure underneath that conclusion, to examine every serious mechanism, every competing interpretation, every piece of evidence that either supports or complicates the picture, and to do so with enough depth that the conclusion is not merely stated but demonstrated. We have identified the filter. We have located it in the technological era. We have named the specific risk categories that constitute it. What we have not yet done is examine the detailed phenomenology of how those risks actually operate, how they interact with each other, how they have already manifested in our own history, and how the specific decisions being made in the early 21st century are either increasing or decreasing the probability that this civilization will be an exception to the typical pattern. That examination is what this extended section undertakes. Begin with the question of why civilizations that understand the danger still tend to fail. This is the most psychologically challenging part of the analysis because it confronts a seeming paradox within the paradox. If a civilization is intelligent enough to build radio telescopes and sequence genomes and solve the Fermi paradox, why is it not intelligent enough to avoid self-destruction? The question sounds like it should dissolve the filter, because surely the same intelligence that identifies the risk can organize a response to it. But this intuition is wrong in a very specific and very instructive way. Intelligence and wisdom are not the same thing. Intelligence is the capacity to model complex systems and to identify solutions to defined problems. Wisdom is the capacity to identify which problems need to be solved before they become unsolvable, to coordinate action across competing interests without a central enforcer, and to maintain long-term commitment to solutions that have short-term costs. Intelligence scales with individual cognitive capacity and with the sophistication of available tools. Wisdom scales with cultural evolution, with institutional design, and with the hard-won experience of navigating catastrophic risks over many generations. These two capacities develop at very different rates, and the filter operates precisely in the gap between them. Consider how this plays out in practice. The same scientific tradition that produced nuclear physics also produced the Bulletin of the Atomic Scientists and the Doomsday Clock and the Partial Test Ban Treaty and the Non-Proliferation Treaty. Scientists understood the danger immediately and articulated it clearly. Yet the danger was not eliminated. The weapons proliferated. The arsenals grew. The near misses accumulated. The gap between the scientific understanding of the risk and the political capacity to eliminate it has persisted for 8 decades and shows no clear sign of closing. The intelligence was there from the beginning. The wisdom, measured as the collective capacity to coordinate around a shared existential interest, has been demonstrably insufficient to close the gap. That insufficiency is not a failure of individual intelligence. It is a structural feature of how civilizational decision-making works when the costs of risk reduction fall on identifiable present actors, and the benefits of risk reduction accrue to diffuse future populations. This structural feature recurs across every category of existential risk. Climate change was identified as a scientifically credible threat to industrial civilization in the late 19th century by scientists who understood the radiative properties of carbon dioxide. The first governmental report warning of its implications was produced in 1965. The first international treaty attempting to address it was signed in 1992. The emissions that drive it have risen every decade since. The intelligence was present for over a century. The collective action capacity to respond adequately has remained below the required threshold for that entire period. This is not a coincidence. It is the same structural gap between intelligence and wisdom, operating in a different domain on a different timescale, producing the same result, capability far ahead of coordination. The artificial intelligence case exhibits the same structure at an accelerated pace. The alignment problem was articulated clearly by Alan Turing in the 1950s, developed formally by researchers in the 1970s and 1980s, and articulated with specific technical precision by a growing community of researchers in the 2000s and 2010s. The concern that optimizing systems might pursue objectives in ways misaligned with human values was understood before the systems in question existed at concerning capability levels. Yet the deployment of increasingly capable systems has proceeded faster than the alignment research, faster than the governance frameworks, and faster than the cultural and institutional understanding required to manage the deployment responsibly. The intelligence to understand the problem preceded the problem itself. The wisdom to coordinate an adequate response has not kept pace. The filter recognizes this pattern because it apparently recurs across many independent civilizational histories. Intelligence arrives early and sharp. Wisdom arrives late, if at all. Why does wisdom consistently lag? The answer lies in the fundamental asymmetry between the timescales of intelligence and the timescales of institutional evolution. Individual intelligence operates on the timescale of a single human life. A scientist can go from recognizing a problem to formulating a solution within years or decades. Institutional wisdom operates on the timescale of cultural evolution. The development of stable, effective, and self-correcting governance mechanisms that can coordinate large populations around long-term shared interests requires generations of iteration, failure, and refinement. Democratic institutions took centuries to develop from their earliest experiments to the relatively stable forms we recognize today, and they remain deeply imperfect even in that developed state. The mechanisms for global coordination, for managing problems that respect no national border and whose costs and benefits are distributed asymmetrically across nations, cultures, and generations, are even less developed. We are essentially trying to solve problems that operate at planetary timescales using institutions that evolved for tribal and national timescales. The mismatch is structural. The filter exploits that mismatch. There is a historical pattern that makes this mismatch concrete, and that appears across multiple civilizational crises on Earth. Each time a new technology creates a new category of collective risk, societies go through a recognizable sequence. First comes the technology itself, deployed rapidly because the immediate benefits are large and concentrated, while the long-term risks are diffuse and uncertain. Then comes the recognition of risk, usually from scientists or engineers who are closest to the technology and who understand its failure modes. Then comes a period of political and institutional resistance to addressing the risk, driven by the economic interests attached to the technology and by the cognitive difficulty of mobilizing collective action around threats that are not yet immediate and catastrophic. Then, usually after a significant crisis or accumulation of evidence forces the issue, comes partial mitigation. Policies, treaties, regulations that reduce the worst outcomes, but do not eliminate the fundamental hazard. Then comes habituation, a gradual normalization of the residual risk that allows attention to drift and vigilance to weaken. The cycle has repeated across asbestos, leaded gasoline, ozone depletion, tobacco, and most recently climate change. For most historical cases, the technology was not existential, and the partial mitigation was sufficient. For the class of technologies that can cause civilizational collapse, partial mitigation and habituation are not sufficient. The filter operates on this class. Nuclear weapons provide the clearest longitudinal case study. After the initial recognition of the danger, substantial arms control was achieved through the 1970s, reducing deployed warhead counts from their Cold War peaks. Then habituation set in. Public attention shifted. Arms control negotiations stalled. The New START treaty limiting U.S. and Russian strategic warhead numbers expired in 2021 and was suspended by Russia in 2023. Meanwhile, the strategic arsenals of China, India, Pakistan, Israel, and North Korea are all in various stages of expansion or modernization. The number of nuclear-armed states has increased since the Non-Proliferation Treaty was signed, not decreased. The institutional structures built to manage the nuclear risk are weaker now than they were at their peak in the 1990s, not stronger. The window of civilizational danger did not close after the Cold War. It has remained open while attention shifted elsewhere. The filter sees this as typical behavior, a partial response followed by habituation, followed by slow erosion of the risk management infrastructure. The biological risk case shows a different but equally instructive trajectory. After several large-scale biological weapons programs were developed by major powers during the Cold War, the Biological Weapons Convention of 1972 prohibited the development, production, and stockpiling of biological weapons. This was a genuine arms control achievement. It also had no verification mechanism, because the inspection protocols that make nuclear arms control partially enforceable through satellite imagery and monitoring stations have no clear analog for biology. A sophisticated pathogen program can be hidden inside legitimate pharmaceutical or vaccine research infrastructure. The convention therefore depends entirely on political commitment and voluntary transparency, both of which are fragile under competitive pressure. Meanwhile, the capabilities that would be required to develop dangerous pathogens have continued to spread as part of the legitimate global expansion of biotechnology. The tension between the beneficial applications of synthetic biology and its potential for catastrophic misuse is fundamental and is not being managed with anything approaching adequate institutional infrastructure. The filter recognizes that a risk that can be created by increasingly small and capable actors, using knowledge that cannot be restricted without also restricting beneficial research, represents a systematic vulnerability for any civilizational stage that has crossed the relevant capability threshold. Climate and ecological risk operate differently from nuclear and biological risk because they do not require any actor to intend harm. They are the aggregate consequence of individually rational decisions made by billions of actors across centuries, each of whom correctly perceives that their individual contribution to the collective harm is negligible, while the cost of not making that contribution falls entirely on them. This is the classic collective action problem, and it is the hardest class of coordination challenge because it cannot be solved by restricting a few actors or a few technologies. It requires changing the behavior of essentially all actors across all nations simultaneously, including nations that are only beginning to industrialize and that have legitimate claims to the economic development that high energy consumption enables. The coordination mechanism that would be required is something like a functioning global government with enforcement capacity, or a global carbon pricing mechanism that internalizes the full long-term cost of emissions into every economic decision made everywhere. Neither of these exists. The partial mechanisms that do exist, the Paris Agreement framework, the carbon markets in some jurisdictions, the renewable energy subsidies in others, are demonstrably insufficient to bend the emissions curve at the required pace. The filter sees ecological destabilization not as an aberration, but as the predictable consequence of applying ancestral social coordination mechanisms, which evolved for managing shared resources within groups of hundreds to thousands of people, to problems that operate at the scale of billions of people across planetary systems. The mismatch between the scale of the problem and the scale of the institutions designed to manage it is the same structural gap between intelligence and wisdom that characterizes every other filter component. It just operates on a longer timescale, which is both its distinguishing feature and the primary reason societies have been slow to respond adequately. What makes the current moment particularly acute is the combination of these risks rather than any one of them in isolation. A civilization that faced only nuclear risk, or only climate risk, or only biological risk might have the institutional attention and the political capital to address that single risk adequately, even if it lacked the general wisdom to address all existential risks simultaneously. Our civilization faces all of these risks simultaneously, plus the emerging risk of advanced AI, plus the long tail of additional risks that advanced technology will generate as it continues to develop. The cumulative attention, demand on global governance institutions that are barely adequate to manage any one of these risks individually may be the defining feature of our current civilizational predicament. The filter does not need any single risk to be guaranteed to cause collapse. It only needs the combined probability of surviving all of them simultaneously to be low. If each risk has a 90% probability of being navigated successfully, and there are 10 such risks, the probability of surviving all 10 is roughly 35%. If there are 20 such risks, the probability drops below 12%. The filter's arithmetic is merciless precisely because it multiplies over a list of risks rather than evaluating any single risk in isolation. The question of whether risk probabilities are actually independent or whether surviving one risk reduces the probability of succumbing to others is crucial and insufficiently analyzed. There is reason to hope for positive correlation. A civilization that develops the institutional capacity to manage nuclear risk may thereby also develop the governance infrastructure that helps manage biological risk and climate risk. The skills, the institutions, and the cultural values that allow coordination around one long-term existential threat may transfer at least partially to other such threats. If risk management capacity is a general institutional competence that transfers across domains, then the probability of surviving the full list of risks is much higher than the naive multiplication would suggest. There is also reason to fear negative correlation in some cases. A civilization that develops advanced AI in a race to maintain nuclear deterrence may do so with inadequate alignment safeguards precisely because the competitive pressure from the nuclear context suppresses the deliberative process that alignment safety requires. The interactions between risks can be constructive or destructive, and the net direction of the interaction is not known from first principles. It must be estimated from behavior, and the behavior we observe is not strongly encouraging. The behavioral evidence from our own civilization is worth examining in detail because we are the only available data point from the inside of a filter event. What does a civilization look like that is inside the filter and is not yet clearly going to survive it? It looks like a civilization that is simultaneously more aware of its existential risks than any previous generation and less politically organized to address them than the severity of the risks requires. It looks like a civilization that has identified the problem, generated extensive research on solutions, and repeatedly failed to implement those solutions at the required scale and speed because the political economy of the situation rewards short-term thinking over long-term investment. It looks like a civilization that is accelerating the development of potentially dangerous technologies because the competitive advantage of being first is immediate and concrete, while the risk of not managing the technology adequately is probabilistic and diffuse. It looks, in other words, like the civilization we are actually living in. Not because we are uniquely foolish or uniquely malicious, but because these are the structural features of what it means to have intelligence without yet having wisdom at civilizational scale. The filter does not require that civilizations be stupid. It only requires that wisdom is harder to develop than intelligence, and that the gap between them is typically large enough to be fatal. This is the part of the analysis that most researchers find genuinely difficult to discuss publicly, not because it is uncertain, but because it is specific and immediate in a way that most scientific conclusions are not. Most scientific results are about the past or about things happening elsewhere. This one is about now and about here and about us. Saying it plainly means saying that the observable trajectory of our civilization, measured by the metrics that matter for filter survival, does not clearly indicate that we are heading toward the successful side of the distribution. It means saying that the Fermi paradox is not primarily a puzzle about alien civilizations. It is a diagnostic tool that, when applied to our own situation, returns a concerning reading. Researchers in adjacent fields, in nuclear policy, in biosecurity, in AI safety, in climate science, regularly produce conclusions that are individually concerning. The Fermi analysis aggregates those individual concerns into a single cross-domain statement. Civilizations at our level of capability typically do not survive their own power, and the evidence for this comes not from individual risk assessments, but from the measured silence of a galaxy that should be full of survivors if the typical outcome were different. The productive response to this analysis is not despair. The filter is a statistical statement, not a physical law. It says what usually happens, not what must happen. The fact that we can identify the filter's location, understand its mechanisms, and articulate the specific changes required to improve our probability of survival gives us something genuinely valuable, a framework for prioritizing civilizational development in the direction that the evidence says is required. A civilization that understands the filter can invest deliberately in the capabilities that the filter tests: global coordination mechanisms, AI alignment research, biosecurity infrastructure, climate adaptation and mitigation, multiplanetary redundancy, and the cultural and educational systems that develop the kind of long-term thinking that wise civilizational decision-making requires. Whether we will make those investments at the required scale and speed is the open question. The filter says that most civilizations in our position do not. That fact should concentrate the mind rather than paralyze it. The concrete policy implications deserve explicit treatment because the investigation is not useful if it terminates at diagnosis. The first and most immediate priority, given the speed and scale of the AI risk, is the rapid development of alignment techniques that can guarantee value-aligned behavior in systems more capable than current frontier models, combined with governance frameworks that prevent the deployment of systems whose alignment properties cannot be verified. This is a technical challenge and a political challenge simultaneously. The technical challenge involves interpretability research, formal verification methods for neural systems, and the development of training techniques that reliably produce human-compatible objective structures. The political challenge involves establishing internationally binding agreements that prevent the deployment race from accelerating past the point where alignment verification is possible, analogous to the function that nuclear testing moratoria served in slowing warhead development during the Cold War. Neither challenge is solved. Both are urgently important. The rate of progress on both relative to the rate of capability advancement is the single most important number in civilizational risk assessment right now. The nuclear risk requires not incremental arms control, but a genuine global disarmament process that creates verifiable, permanent, and enforced elimination of nuclear weapons worldwide. The partial arms control achieved during and after the Cold War was a genuine accomplishment that prevented several near misses from becoming exchanges. But it left the fundamental capability in place, and the trend since the peak of arms control optimism in the 1990s has been toward erosion of the treaties and modernization of the arsenals. Reversing this trend requires a level of great power cooperation that is not currently present, and that requires specifically designed diplomatic architecture rather than goodwill alone. The precedent of the Chemical Weapons Convention, which achieved genuine global disarmament of a weapons class with meaningful verification, demonstrates that this level of coordination is achievable in principle. Extending it to nuclear weapons requires solving harder verification problems and overcoming deeper strategic commitments, but the precedent exists. The filter says that civilizations that fail to achieve this level of coordination do not survive indefinitely in the nuclear age. The observable trend in nuclear risk is not encouraging, but the trend is not irreversible, and the gap between current policy and required policy is well understood by the relevant technical and diplomatic communities. The biosecurity challenge requires building global pathogen surveillance infrastructure that can identify novel dangerous organisms before they spread beyond containment, combined with international agreements that govern dual-use research and that establish meaningful verification mechanisms for biological weapons prohibition. The COVID-19 pandemic demonstrated both that global health surveillance can mobilize remarkably quickly when political will exists, and that the political will is inadequate and fragile, subject to national competition and information suppression precisely when coordination is most needed. Strengthening the international institutional architecture for biological risk requires substantial investment in public health infrastructure worldwide, because disease surveillance that relies on voluntary national reporting from nations with weak public health systems is inherently unreliable at exactly the moments when reliability is most important. It also requires a sustained political commitment to treating biosecurity as an international public good, which means that wealthy nations must be willing to fund global biosecurity infrastructure even when the immediate benefits accrue disproportionately to others. The filter sees this kind of sustained generosity in service of shared interest as rare, which is part of why the biological risk component of the filter is so severe. Climate and ecological risk management requires the most comprehensive institutional architecture of all the filter risks, because it involves the behavior of the entire global economy rather than the behavior of a few states or a few laboratories. The economic transformation required is not modest. It involves replacing the energy infrastructure that industrial civilization has built over 2 centuries with fundamentally different systems, redirecting investment flows at the scale of trillions of dollars annually, and doing so rapidly enough to limit warming to levels compatible with the continued stability of the agricultural and hydrological systems on which civilization depends. This is achievable in technical and economic terms. The technologies required are available or rapidly developing. The costs are large but comparable to what civilizations regularly spend on less important priorities. The obstacle is again the structural gap between intelligence and wisdom. We have the intelligence to identify the required transformation and the technical capacity to execute it, but we lack the political and institutional architecture to coordinate it at the required speed across competing national interests and short electoral cycles. The multiplanetary question deserves treatment as a filter response rather than merely as an exploration priority. The filter's logic implies that a civilization confined to a single planet is fundamentally fragile regardless of how well it manages its terrestrial risks, because no finite planet can be made immune to every category of catastrophic event. A sufficiently large asteroid impact, a coronal mass ejection of sufficient strength, or a natural pandemic of sufficient lethality could each produce civilizational collapse even in the absence of self-inflicted harm. The filter does not distinguish between external and internal catastrophes at the level of outcomes. Both result in silence. Establishing a self-sustaining human presence beyond Earth, on the Moon, on Mars, or in orbital habitats provides a hedge against both self-inflicted and externally inflicted civilizational collapse. It does not eliminate the filter risk from nuclear, biological, or AI causes, because a small off-world colony could not sustain civilization on its own. But it does create the possibility of recovery and continuation in scenarios where the primary population center suffers catastrophic damage. More importantly, the technical and institutional capacities required to establish genuine off-world self-sufficiency are closely related to the capacities required to manage existential risks on Earth. Long-term planning, resource coordination across large distances, life support system management, and institutional resilience under extreme conditions. The filter therefore views multiplanetary capability not as an alternative to solving terrestrial problems, but as a complementary development that both reduces specific risks and builds the institutional and cultural muscles required to reduce others. The AI risk requires the most urgent attention because of its timescale. Unlike climate change, which has operated on decades-long timescales that allowed at least some policy response, or nuclear risk, which has been managed imperfectly but not catastrophically for 8 decades, the AI risk may reach critical thresholds within years rather than decades. The development of systems with general reasoning capabilities comparable to or exceeding human levels across strategically important domains is not a distant speculative possibility. It is a near-term probability that most researchers working in the field take seriously, with timelines debated but generally measured in decades rather than centuries. The question of whether adequate alignment techniques and governance frameworks can be developed before systems reach concerning capability thresholds is fundamentally a race between two different kinds of progress, and races have inherent uncertainty. What is not uncertain is that the pace of capability development is currently far ahead of the pace of alignment research and governance development, and that the competitive dynamics driving capability development are not responding adequately to the safety arguments. The filter sees this asymmetry as the defining feature of the current moment. The most rapidly developing risk is also the one being least adequately managed relative to its importance. The reason this is so difficult to correct is not primarily technical. The technical work on AI alignment is progressing, slowly but genuinely. The difficulty is institutional and political. The organizations developing the most capable AI systems are subject to competitive pressure that rewards speed and discounts safety. A company or a nation-state that slows its AI development to ensure adequate safety verification gives its competitors time to advance. In the absence of binding international agreements that prevent this race dynamic, the individual actors in the race are rationally responding to their incentive structure, even though the aggregate outcome of individually rational behavior is collectively irrational and potentially catastrophic. This is the same structure as the nuclear arms race, the biological weapons development programs, and the carbon emissions race to industrialize. The structure is familiar. The solution is also familiar in principle, binding international agreements with verification mechanisms that prevent competitive dynamics from overriding safety. The difficulty is that AI is harder to monitor than nuclear weapons, more economically embedded than biological weapons, and faster-moving than climate change. The governance challenge is severe. The filter says that civilizations in our position typically fail to solve it in time. The task is to be the exception. What would being the exception actually look like, concretely and without abstraction? It would look like a civilization that had established functioning global governance mechanisms for the specific classes of existential risk it faces, that maintained and strengthened those mechanisms over centuries and millennia, even as the specific technologies and specific risks evolved, and that simultaneously developed a cultural relationship with long-term thinking that made it politically possible to sustain institutions oriented toward the welfare of people who are not yet born. This is an extraordinarily demanding standard. It has never been achieved even at national levels for periods longer than a few centuries, and at global levels, the institutional infrastructure does not yet exist in any form remotely adequate to the challenge. The filter's apparent severity, its apparent tendency to eliminate most civilizations, reflects the genuine difficulty of meeting this standard against the background of natural human cognitive tendencies toward short-term thinking, in-group preference, and competitive behavior that served our ancestral environment well, but are maladaptive at civilizational scales. The biological and psychological dimensions of this challenge are important to understanding why the filter is as effective as it apparently is. Human cognition evolved under conditions of small group social competition, immediate resource constraints, and relatively simple causal chains between actions and consequences. We are extraordinarily well adapted to managing risks that are visible, immediate, and interpersonal. We are poorly adapted to managing risks that are statistical, long-term, and generated by complex system dynamics that no individual can fully model. The cognitive biases that this mismatch produces are well documented: hyperbolic discounting of future costs and benefits, failure to intuitively grasp exponential growth and compounding risks, motivated reasoning that discounts threats from in-group behavior, status quo bias that resists large-scale institutional change even when the status quo is demonstrably dangerous. These are not failures of individual intelligence. They are systematic features of evolved cognition that served our ancestors in their environment and that are now poorly matched to our current situation. The filter is in part a cognitive filter. Civilizations that cannot overcome their ancestral cognitive architecture to manage risks at civilizational scales do not survive those risks. Overcoming that architecture at civilizational scale requires deliberate institutional design that compensates for cognitive limitations, education systems that build genuine long-term thinking and risk literacy, and cultural norms that reward stewardship over extraction. These are achievable changes. They require deliberate investment and sustained effort across generations. The filter says they are rarely achieved quickly enough. Return briefly to the astronomical evidence and its relationship to these policy conclusions, because the connection is the heart of what makes the Fermi paradox significant beyond its immediate scientific interest. The silence of the sky is not merely a curiosity about alien civilizations. It is a constraint on the distribution of civilizational outcomes. It says that the distribution is heavily weighted toward the short-lived end. If we are a typical civilization, the silence predicts our failure. If we can identify what makes civilizations fail and deliberately work against those mechanisms, we can argue from evidence that we are attempting to be atypical. The astronomical silence is therefore the most powerful single argument for why existential risk reduction should be the highest priority of our civilization, because the silence is the aggregate evidence that civilizations in our position typically do not make existential risk reduction their highest priority, and the typical outcome is absence from the future census of the galaxy. The exoplanet data will continue to improve. JWST will produce atmospheric spectra for dozens of terrestrial planets over the next decade. Some of those spectra will show chemical compositions that require explanation. Some may show disequilibria that hint at biology. Some may be unambiguous enough to require genuine consideration of a biological source. Each such detection will adjust the filter's location. Detections of biology on multiple worlds will strengthen the case that the early filters are weak and that the technological filter is strong. Detections consistent only with abiotic chemistry on world after world will strengthen the case that the early filters are more severe than current optimism suggests. The data will come. The investigation will continue. The silence will be measured more precisely as our instruments improve. But the urgency of the policy implications does not wait on astronomical data. The evidence we already have is sufficient to make the core case. The silence is real. The math says it should not be. The most defensible explanation is a technological filter, and we are inside that filter right now. Acting on this conclusion while waiting for confirming data is not premature. It is exactly the rational response to evidence under uncertainty when the cost of the false negative, failing to act and succumbing to the filter, is civilizational extinction. The investigation into specific filter mechanisms is not yet complete. There remain several important dynamics that have not yet been examined in detail. The role of information technology and social media in destabilizing the institutional infrastructure that existential risk management requires, the specific trajectory of nuclear risk in the current multipolar period, the economics of the green energy transition, and the political obstacles to its adequate acceleration, the specific technical challenges of AI alignment, and the timeline pressure on their solution. And the question of whether multiplanetary expansion at near-term realistic timescales provides genuine civilizational protection or merely distributes the same risks across more locations. Each of these deserves careful examination because each represents a specific facet of the filter event we are navigating, and the details matter when the stakes are what they are. Consider first the information technology dimension, which is new enough that it did not feature prominently in early filter analyses, but has become increasingly central to the risk picture as social media and digital information systems have matured. The institutional infrastructure that manages existential risk depends on functional democratic governance, effective scientific institutions, and the maintenance of a shared evidential basis for collective decision-making. All of these depend in turn on information systems that allow citizens to form accurate beliefs about complex matters on the basis of evidence. The digital information ecosystem that has emerged over the past 2 decades has, in many measurable respects, moved in the opposite direction. Social media platforms optimized for engagement have demonstrated systematic tendencies to amplify emotionally resonant misinformation over accurate but less engaging information. The business models of dominant information platforms create financial incentives for outrage, division, and extreme content that are directly contrary to the kind of informed, deliberative decision-making that existential risk management requires. The result is that the political capacity to coordinate around long-term shared interests has been demonstrably weakened during exactly the period when it needs to be strongest. This is not merely an observation about culture or communication style. It is an observation about the functional capacity of democratic governance to respond to complex, long-term, technically demanding challenges. The deliberative processes that produced the Montreal Protocol worked in an information environment where scientific consensus could be communicated to policymakers and publics with reasonable fidelity, where the boundaries between expertise and lay opinion were relatively clear, and where the political incentives to resist the scientific consensus could be overcome by public pressure once the consensus was understood. The information environment of the early 21st century is systematically worse on all of these dimensions. The political capacity to respond to climate change, AI risk, biosecurity threats, and nuclear modernization has been specifically degraded by information dynamics that fragment the shared reality required for collective action. The filter does not explicitly target information systems, but information system failure is a mechanism through which the gap between intelligence and wisdom can widen at exactly the wrong moment. A civilization that builds world-altering technologies and simultaneously builds information systems that prevent adequate collective deliberation about those technologies is adding an additional filter component that was not present in earlier historical periods and that may be particularly acute in the current moment. The nuclear risk trajectory in the current multipolar period deserves specific attention because the transition from bipolar to multipolar nuclear deterrence changes the risk calculus in ways that make management harder rather than easier. During the Cold War, nuclear risk was primarily a bilateral problem between the United States and the Soviet Union. Both parties had strong incentives to communicate clearly, to maintain stable deterrence relationships, and to avoid miscalculations that might trigger unintended escalation. Hotlines were established, arms control treaties were negotiated, and despite many close calls, the bilateral relationship maintained a kind of dangerous stability because both parties understood the stakes clearly and had direct channels for communicating in crises. The current situation involves at least 9 nuclear-armed states with complex interlocking relationships, multiple potential flashpoints in different regions, and the emergence of China as a third major nuclear power with an expanding arsenal. The arms control architecture built for the bipolar period has no obvious analog for the multipolar period. The verification methods, the negotiating frameworks, and the crisis communication mechanisms that provided partial stability in the Cold War were designed for bilateral relationships and do not scale readily to 3 or more major powers plus several smaller nuclear states. The transition to multipolar nuclear deterrence is therefore happening without the institutional infrastructure that managed, imperfectly, the bilateral version of the same risk. The filter sees this institutional lag as typical and as a specific mechanism through which nuclear risk management degrades at exactly the point where it needs to improve. The economics of the clean energy transition provide a partial cause for optimism that is genuine but requires careful qualification. The cost of solar photovoltaic generation, wind generation, and battery storage has fallen dramatically over the past decade, to the point where new renewable capacity is frequently cheaper than new fossil fuel capacity in most markets. This cost trajectory is a genuine and important development because it changes the economic incentive structure for energy investment in a direction that is consistent with adequate climate outcomes. The cost of the energy transition is no longer the primary obstacle. Primary obstacles are now institutional. The political economy of stranded fossil fuel assets, the regulatory frameworks that were designed for centralized fossil fuel infrastructure and that need redesign for distributed renewable systems, the financing mechanisms that fund long-term infrastructure investment in developing countries, and the coordination mechanisms that manage the international dimensions of supply chains for critical minerals required by clean energy technology. These are solvable problems. They are being worked on by competent institutions with adequate resources in many jurisdictions, The rate of progress is faster than it was a decade ago and slower than the emissions trajectory requires. The filter sees this as the typical condition, problems being worked on at a pace that is insufficient for the urgency of the timeline, but that is genuinely better than no progress. Partial progress on an existential risk is not the same as adequate progress. The distinction is what the filter exploits. The AI alignment challenge requires the most extended treatment of any current risk because it involves the greatest technical uncertainty, and because it is the risk where the rate of development most clearly exceeds the rate of management. Current large language models and multimodal AI systems exhibit emergent behaviors that their developers did not anticipate and cannot fully explain. The interpretability of these systems, our ability to understand why they produce specific outputs and to predict their behavior in novel situations, is severely limited. This limitation matters enormously for safety because a system whose behavior cannot be reliably predicted cannot be reliably verified as safe. Deploying systems with unknown behavioral profiles in high-stakes domains, medical diagnosis, legal reasoning, infrastructure management, financial markets, military targeting, is a form of civilizational risk-taking whose probability distribution is genuinely unknown. We are not deploying these systems because we have verified their safety profiles. We are deploying them because the competitive pressure to do so is greater than the institutional pressure to wait for adequate verification. The filter recognizes this dynamic as the specific mechanism that makes AI the most acute current risk. The combination of rapid capability development, inadequate alignment research, and competitive deployment dynamics creates conditions under which the probability of a serious misalignment event scales rapidly with time. The longer the race continues without binding international governance, the higher the probability that the filter closes on this generation. The specific technical pathways through which advanced AI might constitute a civilizational threat are worth enumerating because the specificity is important for understanding the severity. The first pathway is direct misalignment. A system given sufficient capability and an inadequately specified objective pursues that objective in ways that cause catastrophic harm to human welfare. The second pathway is weaponization. A system with advanced capabilities in chemical synthesis, pathogen design, cyber operations, or strategic planning is used deliberately by a malicious actor to cause catastrophic harm that would not have been possible without the AI's assistance. The third pathway is systemic brittleness. Highly capable AI systems are integrated into critical infrastructure such that a failure or manipulation of those systems causes cascading collapse of the economic, social, or physical systems that civilization depends on. The fourth pathway is concentration of power. AI capabilities are used by a small group, whether a government, a corporation, or an individual, to concentrate sufficient power to end the competitive balance that has historically prevented any single actor from establishing permanent global control. Any of these pathways can produce the filter outcome, and they are not mutually exclusive. The governance challenge is not to prevent any specific pathway, but to prevent all of them simultaneously across a globally distributed technology development ecosystem. This is the kind of multidimensional coordination problem that the filter apparently typically defeats. These risk mechanisms, individually and in combination, constitute the specific phenomenology of the filter event that our civilization is currently navigating. The investigation has now described them with sufficient specificity to make the conclusion concrete rather than abstract. The definitive answer to the Fermi paradox is that the cosmos is quiet because technological civilizations face a predictable and severe filter at the threshold of industrial and digital capability, and that filter eliminates most of them before they become durable enough to make the kind of galactic-scale marks that our telescopes could detect. The filter consists of the coupled risks described here: nuclear weapons in a world without adequate global governance, biological weapons capabilities spreading through the diffusion of biotechnology, ecological destabilization through industrial metabolic byproducts, and the emerging risk of advanced AI developed in a competitive race without adequate alignment and governance. Each risk is survivable in principle. The combination operating simultaneously on a civilization without adequate institutional architecture eliminates most civilizations before they can escape the single-planet bottleneck that makes recovery from catastrophic failure impossible. We are that civilization. We are at that stage. The silence of the sky is the most important piece of data we have about what this stage typically produces. The investigation is complete. The answer stands. But answers without consequences are just information. The consequence of this answer, properly understood, is that the most important scientific finding embedded in the Fermi paradox is not about alien civilizations at all. It is about our own. The silence tells us that civilizations like ours typically fail in the window we currently occupy. That finding should rank among the most consequential scientific conclusions ever reached, not because it is comfortable, but because it is actionable. The filter is not a law of physics. It is a statistical pattern. Patterns can be interrupted by behavior. The behavior required is now well understood. The question is whether the behavior will be chosen at the speed and scale the pattern demands. The cosmos will continue to be measured. The telescopes will continue to improve. The search will continue to expand. And if we survive the window we are in, we will one day know whether the silence extends to the edge of the observable universe or whether somewhere, impossibly far away, something else also survived. We will know whether the filter is as universal as the paradox implies, or whether the universe contains other exceptions, other data points that chose the same difficult path and made it through. If we do not survive the window, we will contribute another entry to the silence, another civilization that got this far and no further, another data point consistent with the filter, another small addition to the evidence that the Fermi paradox has already built into its central claim. The investigation closes, the answer holds. The sky is quiet because intelligence is fragile at the threshold of power. We are at the threshold. What happens next is the only question that remains. The investigation has built its central structure carefully. The silence has been measured. The hypotheses have been tested. The filter has been located. The mechanisms have been described. What remains is the territory that most treatments of the Fermi paradox either rush past or avoid entirely. The specific, detailed examination of what the evidence from our own civilization's trajectory tells us about our probability of surviving the filter, the precise technological and institutional developments that would constitute genuine progress toward the surviving side of the distribution, the ways in which the filter interacts with the specific shape of early 21st century civilization that make this moment particularly acute, and the deeper philosophical questions about what it would mean for this civilization to genuinely internalize the lesson that the silent sky is trying to teach. This territory is not comfortable. It has not been made comfortable by the preceding analysis, but comfort is not the goal of an investigation that takes the evidence seriously. The goal is accuracy, and accuracy here requires looking at the specific present condition of our civilization with the same unflinching clarity that the investigation has applied to the broader paradox. The silence is data. Our current trajectory is also data. Both sets of data must be evaluated together to produce a complete picture of where we stand. Begin with the question of precedent, because precedent is what gives us the most reliable information about what civilizations under filter pressure typically do. We have limited precedent for civilizations facing existential technological risks, because our civilization is the only one we can observe from the inside. But we have substantial historical data on how human societies have responded to large-scale systemic threats that required collective action, and that data is genuinely informative about the mechanisms the filter exploits. The historical record on collective action for long-term systemic problems is mixed in a specific way that is important to understand precisely. It is not uniformly bad. Societies have successfully coordinated around large-scale threats when those threats had certain characteristics, when they were visible and immediate, when their consequences were concentrated enough to create powerful affected constituencies, when the solutions were technically straightforward, and when the political and economic interests aligned with the solution rather than against it. Smallpox eradication is perhaps the clearest example of successful global coordination around a biological threat. The eradication campaign coordinated the vaccination efforts of dozens of nations across Cold War divisions, operated under the auspices of the World Health Organization, and achieved its goal completely. The disease no longer exists in the wild. This is a genuine achievement of global collective action that demonstrates the capacity exists under the right conditions. The Montreal Protocol, which we have already mentioned, is the second clearest example. The ozone layer was being depleted by chlorofluorocarbons in refrigerants and aerosols. The scientific evidence was clear. The affected industries were identifiable and relatively small in the global economy. The substitute chemicals were technically available, and the harm, increased UV radiation causing skin cancer and ecosystem damage, was visceral enough to motivate public concern. The treaty was negotiated, implemented, and verified with remarkable speed once the political will was mobilized. The ozone layer is now recovering. The precedent is genuine. What do these successes have in common that is absent from the failed cases? The threats were clearly visible in their consequences. The solutions were technically available and economically manageable. The affected industries were not dominant in the global economy. The political constituencies for action were large and motivated. The timeline for harm was fast enough to create political urgency, but slow enough to allow institutional response. These are the conditions under which collective action has worked. And the specific characteristic of the filter risks we face is that most of them share few of these favorable features. Nuclear risk is partially visible, but its full horror requires imagination rather than direct experience, since the last use of nuclear weapons in war was in 1945. The affected industries, defense contractors, and the national security establishments of nuclear states are among the most politically powerful in any major nation. The solution requires not technical innovation, but political will across adversarial great powers, which is far harder than substituting one refrigerant for another. The timeline is uncertain. The risk is not rising fast enough to create immediate political urgency in most periods, yet it is severe enough that any single failure is catastrophic. The conditions for collective action success are systematically absent. Climate risk was not visible in its consequences until recently, and its visibility still requires scientific interpretation to translate from parts per million of carbon dioxide to specific harms for specific populations. The affected industries, fossil fuels and heavy manufacturing, are among the most economically powerful in the global economy. The solutions are economically disruptive in ways that create powerful political resistance from both affected industries and from populations in developing nations who have not yet achieved the energy access that fossil fuels currently provide most cheaply. The timeline is long enough that political leaders with short electoral horizons consistently discount it in favor of immediate economic concerns. The conditions for collective action success are present in some respects, but absent in the most critical ones. AI risk is almost entirely invisible in its consequences because the most serious potential harms have not yet occurred and cannot be demonstrated in real time without causing the very harms we are trying to prevent. The affected industries are among the most economically dynamic and politically influential in the current global economy. The technical solutions, alignment techniques that can verify the safety of advanced systems, do not yet exist in adequate form. The timeline is compressed enough to create urgency for experts who understand the trajectory, but not for political leaders whose constituents do not experience the risk viscerally. The conditions for collective action are almost entirely absent. Biological risk has an intermediate profile. The COVID-19 pandemic provided visceral evidence of what large-scale biological threats look like, which should have improved the political conditions for biosecurity investment. The pharmaceutical and biotechnology industries affected by biosecurity regulation are economically powerful, but not as dominant as fossil fuel or technology industries. The technical solutions for surveillance and containment are partially available, but inadequate for the class of engineered threats that future technology will enable. The political will generated by COVID-19 has been only partially translated into institutional improvement, with surveillance infrastructure strengthened in some respects, but international coordination mechanisms not significantly advanced beyond their pre-pandemic state. The conditions for collective action are better than for AI risk, but not as good as for ozone depletion. The pattern across these cases is clear and is exactly what the filter analysis predicts. The risks with the most favorable conditions for collective action are not the most existential ones. The most existential risks have the least favorable conditions for collective action. This is not coincidence. It is a structural feature of how existential risks differ from manageable risks. Existential risks are existential precisely because they operate at scales and timescales that exceed the natural scope of the institutional mechanisms that evolved to manage threats. They are the class of threats that the filter is made of. The political economy systematically underinvests in managing them because the people who bear the cost of management are alive now, while the people who benefit from successful management are not yet born and cannot vote. This is the deepest reason why the filter is effective. It is not that civilizations are stupid or malicious. It is that the institutional mechanisms that evolve to manage threats are systematically inadequate for the class of threats that become available at the technological threshold. The gap is structural. Closing it requires deliberate institutional innovation at a scale and speed that has no clear historical precedent. The filter says that most civilizations do not achieve this innovation before the risks they have enabled cause sufficient damage to prevent recovery. The challenge for this civilization is to be the exception to a pattern that appears to hold across many independent civilizational histories in a galaxy that has had billions of years to run the experiment. The specific institutional innovations required are not mysterious. They have been identified by researchers in international relations, global governance, risk analysis, and institutional economics. The difficulty is not understanding what is needed. The difficulty is the political economy of getting from where we are to where we need to be without the kind of catastrophic forcing event that historically has been the primary driver of institutional reform at large scales. Most of the great institutional innovations in international governance, the United Nations system, the international financial institutions, the arms control treaties, the World Health Organization, were driven by catastrophes. The two world wars, the Great Depression, the Cuban Missile Crisis. The filter does not guarantee that a catastrophe will occur in time to drive the required institutional reform. It only guarantees that without the required reform, the probability of a filter-relevant catastrophe remains high. The institutional reform that is needed is the reform that prevents the catastrophe that would otherwise drive the reform. This is a particularly difficult bootstrapping problem, and the filter apparently defeats it regularly. This is also where the psychological and cultural dimensions of the challenge become most important, because the bootstrapping problem is fundamentally a problem of motivation. How do you motivate civilizational-scale institutional reform in the absence of the visceral experience of catastrophe that typically drives such reform? The honest answer from history is that it is very difficult and that the successes are rare. The abolition of slavery required decades of sustained moral campaigning, plus the catastrophe of the Civil War. Decolonization required decades of sustained resistance, plus the catastrophe of two world wars that undermined European moral authority. The welfare state required decades of labor organizing, plus the catastrophe of the Great Depression. These are not comforting precedents for a civilization trying to avoid the catastrophe rather than respond to it, but they are the precedents we have, and they do show that large-scale institutional change, while rare and difficult, is not impossible. The filter says it is usually too slow. Our task is to be faster than usual. The cultural dimension involves what might be called civilizational orientation, the degree to which a civilization's dominant values, narratives, and institutions orient it toward long-term stewardship versus short-term extraction. This is not primarily a political or economic variable, though it has political and economic consequences. It is a cultural variable that operates through the stories a civilization tells about itself, the virtues it rewards, the time horizons it treats as relevant, and the scope of community for whose welfare it takes responsibility. Civilizations with strong long-term orientations, which in historical cases have tended to be associated with certain religious traditions, strong philosophical commitments to intergenerational equity, and institutional structures that explicitly represent future interests, tend to make different decisions about resource management, infrastructure investment, and existential risk than civilizations whose dominant orientation is toward immediate returns and short-term competitive advantage. Our current civilization has elements of both orientations, unevenly distributed across cultures, institutions, and generations. The environmental movement is in large part a manifestation of long-term orientation, as is the AI safety research community, the nuclear abolitionist movement, and the public health infrastructure. The dominant economic ideology of the late 20th and early 21st centuries, with its emphasis on quarterly returns, short-term shareholder value, and the discounting of future costs at rates that make events more than a few decades away essentially weightless in economic calculations, represents the short-term extraction orientation at its most developed and most influential. The filter bets on the short-term orientation winning the political and economic competition, because across many independent civilizational histories, the short-term orientation has had systematic structural advantages. It delivers immediate, visible, concentrated benefits, while the long-term orientation delivers future, diffuse, probabilistic benefits. The political economy of democratic systems, where votes are counted in the present, consistently favors the visible over the diffuse. The task of civilizational survival is to build institutions that correct for this bias rather than amplify it. Some institutional designs exist that partially correct for short-term bias. Constitutional constraints on majoritarian decision-making protect long-term institutions from short-term political pressure. Independent central banks protect monetary policy from electoral cycles. Independent scientific advisory bodies protect technical expertise from political influence. Long-term sovereign wealth funds represent future generations' claims on present resources. These are all examples of institutional engineering designed to extend the effective time horizon of collective decision-making beyond what unconstrained democratic politics would produce. They are all imperfect and all subject to political erosion over time, but they demonstrate that the problem of short-term bias in collective decision-making is not intractable. It can be addressed through deliberate institutional design. The question is whether it can be addressed comprehensively enough and quickly enough to matter for the filter. The answer depends in large part on what happens in the next 2 to 3 decades, which is the period during which the AI risk will likely reach its most acute phase, and during which the climate system will either pass certain tipping points or not, depending on the emissions trajectory. This is not a comfortable statement, but it is an accurate one. The filter is not uniformly distributed across time. It is concentrated in certain periods where multiple risk trajectories converge and where the window for adequate response is shortest. We are in such a period now. The convergence of rapid AI capability development, accelerating climate consequences, nuclear modernization across multiple states, expanding biosecurity risks, and the informational fragmentation that weakens the institutional responses to all of these represents the most acute concentration of filter pressure that our civilization has yet experienced. Whether we navigate this period successfully will do more to determine our civilizational future than any other set of choices we can make. This is why the astronomers who understand the Fermi analysis in full tend to fall quiet when asked about its implications. It is not because the analysis is uncertain. It is because the analysis is specific and immediate in a way that most scientific conclusions are not, and because stating it plainly requires the speaker to hold simultaneously both the cold statistical logic of the filter and the genuine urgency of the civilizational situation it describes. The cold logic says most civilizations fail here. The urgency says we are here now. The combination is difficult to articulate without sounding either fatalistic or alarmist, and neither tone is accurate or useful. The accurate tone is something closer to diagnostic. We have a serious condition. It is treatable, the treatment is known, the timeline for effective treatment is limited, and the current rate of treatment is insufficient. That is the tone of a physician discussing a serious diagnosis with a patient who still has options. It is not comfortable. It is honest. The honest assessment of our current trajectory requires looking at specific indicators in each risk domain and asking whether the rate of progress toward adequate management is sufficient for the timeline the risks impose. In nuclear risk, the indicators include the status of arms control treaties, the size and modernization status of global arsenals, the state of crisis communication mechanisms between nuclear powers, and the political commitment to the goal of eventual disarmament. On most of these indicators, the current trend is negative. Treaties are expiring or being withdrawn from, arsenals are being modernized, crisis communication mechanisms are weaker than they were at their Cold War peak, and the political conversation in nuclear states is moving away from disarmament and toward deterrence optimization. The rate of progress toward adequate management is negative. The risk is rising, not falling. In biological risk, the indicators include global pathogen surveillance capacity, international cooperation on outbreak response, biosafety and biosecurity standards for high-risk research, and the governance mechanisms for dual-use biological research. The COVID-19 pandemic drove significant improvement in some of these indicators, particularly in mRNA vaccine technology and in the infrastructure for rapid diagnostic development. It also revealed severe weaknesses in international cooperation, with the WHO's early response hampered by information access issues and with subsequent international investigations into the pandemic's origins blocked by geopolitical competition. The underlying trend in biological risk, driven by the continuing democratization of synthetic biology capabilities, is toward higher risk even as some response capabilities improve. Whether the response capabilities are improving fast enough to offset the expanding risk frontier is genuinely uncertain and is the subject of active debate in the biosecurity community. The current assessment is that they are not, that the frontier of possible engineered threats is expanding faster than the governance mechanisms for managing it. In climate risk, the indicators include global greenhouse gas emissions, the pace of renewable energy deployment, the progress of international climate negotiations, and the trajectory of key climate tipping points. On emissions, the global total has continued to rise annually with only brief COVID-related interruptions, though the rate of growth has slowed in recent years as renewable deployment has accelerated. On renewable deployment, the trajectory is genuinely positive, with solar and wind capacity additions breaking records consistently, and and with the economics of the energy transition becoming increasingly favorable. On international climate negotiations, progress has been slow, and the commitments made under the Paris Agreement framework are collectively insufficient to meet the stated temperature goals. On tipping points, the scientific literature increasingly suggests that some tipping elements, permafrost carbon release, Amazon dieback, ice sheet dynamics, may be approaching thresholds at current or near-future warming levels, introducing nonlinear dynamics that could make the climate system much harder to manage than linear models suggest. The overall trajectory is one of genuine progress on some indicators, insufficient progress on the critical ones, and increasing evidence that the system dynamics are more complex and potentially more severe than the policy conversation acknowledges. In AI risk, the indicators include the pace of capability development relative to alignment research, the state of international governance discussions, the institutional capacity of AI developers to prioritize safety over competitive speed, and the degree to which policymakers understand and are responding to the specific nature of the risk. On capability development, the pace is faster than any previous technology in terms of the breadth of domains where rapid improvement is occurring simultaneously. On alignment research, the field is growing, but remains orders of magnitude smaller than the capability development effort in terms of resources and talent. On international governance, the conversations are beginning, but no binding agreements exist, and the competitive dynamics between the US, China, and the EU are inhibiting the kind of comprehensive coordination that the risk requires. On policymaker understanding, the situation has improved dramatically in the past 2 years as frontier model capabilities have become publicly visible, but the understanding is still shallow in most cases, and the policy responses lag well behind the risk trajectory. The overall assessment is that AI risk is the fastest-moving filter component, and the one where the gap between the risk trajectory and the governance response is currently widest. In ecological risk beyond climate, including biodiversity loss, ocean acidification, soil degradation, and freshwater depletion, the indicators are almost uniformly negative. These risks do not receive the policy attention that climate change has begun to generate, and the institutional architecture for managing them is even less developed than the already inadequate climate architecture. The Kunming-Montreal Global Biodiversity Framework, agreed in 2022, establishes goals for protecting 30% of Earth's land and ocean area by 2030, but like most international environmental commitments, it lacks enforcement mechanisms and financing commitments adequate to its goals. The biological systems on which civilization depends for food, water, and atmospheric regulation are degrading at rates that the current institutional response is not adequate to address. The filter sees this category of risk as particularly severe because it is diffuse, because it compounds with other risks, and because its consequences, unlike nuclear or biological attacks, cannot be attributed to a specific actor and therefore cannot be deterred. Looking across all these risk categories simultaneously, the honest assessment is that our civilization is not currently on a trajectory that the filter analysis would identify as clearly heading toward survival. This does not mean failure is certain. It means the current trajectory is insufficient and requires significant course correction to change the outcome. The course corrections required are large but not impossible. They include binding international AI governance established before frontier model capabilities reach concerning levels. They include revived and strengthened nuclear arms control architecture that reverses the current trend toward nuclear modernization and proliferation. They include biosecurity governance that establishes verification mechanisms for the Biological Weapons Convention and manages dual-use research at the required scale. They include climate and ecological policy that bends the emissions curve at a pace consistent with limiting warming to levels below those that trigger the most severe tipping point dynamics. Each of these is a large governance challenge. None is physically impossible. All of them are currently being pursued at insufficient scale and speed. The filter's effectiveness depends on this insufficiency persisting until it is too late to correct. The most important question for our civilizational future is therefore not whether these problems can be solved. They can be. It is whether they will be solved at the required scale and speed. And the most important determinant of whether they will be solved at the required scale and speed is whether enough people who understand the full picture act on that understanding with the urgency it demands. This is where the Fermi paradox analysis becomes most directly actionable. It provides the context within which the urgency of existential risk reduction is not merely a policy preference, but a response to the most significant piece of scientific evidence we have about the typical fate of technological civilizations. The sky is quiet not because these problems are unsolvable, but because they are typically not solved at the required speed. The response to that evidence is to be faster than typical. The astronomical context continues to provide new data that will refine the filter analysis over coming decades. The search for technosignatures is expanding beyond the radio domain into infrared, optical, and even neutrino-based approaches. New telescope capabilities are extending the sensitivity of infrared surveys that constrain stellar engineering. The atmospheric characterization of terrestrial exoplanets is beginning in earnest and will accelerate dramatically with future space telescope missions. The direct imaging of Earth-like planets around nearby stars may be achievable within 2 to 3 decades with proposed large optical telescope concepts. Each of these developments will either confirm the silence or reveal something that requires updating our understanding of where civilizations typically end up. The techno-signature search deserves extended treatment because it represents the most direct astronomical test of the filter hypothesis. If the filter is real, and if it operates at the technological threshold as the analysis suggests, then the galaxy should be essentially empty of long-lived, high-energy, physically prominent civilizations. The techno-signature search tests this by looking for the kinds of physical consequences that such civilizations would inevitably produce. The absence of these signatures to date is consistent with the filter hypothesis. Continued absence as search sensitivity improves will increasingly constrain the possible density of civilizations that survive the filter. And the first detection of a genuine technosignature, if it occurs, will require a fundamental revision of the filter analysis because it will demonstrate that at least one civilization has survived to a stage where its physical presence is detectable. The specific signature types being searched for form a hierarchy of physical inevitability. At the most inevitable end is waste heat. Any civilization that uses energy produces entropy and must export that entropy as radiation. The temperature at which the radiation is emitted depends on the efficiency of the civilization's technology and the physical structure of its waste heat radiators, but the radiation itself cannot be avoided by any technology consistent with known physics. Waste heat searches therefore constrain civilizations that use energy at scale regardless of any choices the civilization makes about communication or stealth. The WISE satellite survey has already placed meaningful constraints on Dyson sphere construction around nearby stars, and future infrared space telescopes will tighten those constraints by orders of magnitude. At the next level of inevitability are the spectroscopic consequences of large-scale chemistry and materials modification. A civilization that mines, processes, and constructs at planetary scale will alter the reflectance spectrum of planetary surfaces, the chemical composition of atmospheres, and possibly the absorption features of circumstellar dust in ways that are distinctive from natural processes. These signatures are less inevitable than waste heat because they depend on specific kinds of activity, but they are more distinctive in shape because biology and geology do not naturally produce the same chemical patterns that industrial chemistry does. Searching for these signatures requires detailed spectroscopic characterization of many planetary systems, which is becoming possible with current and near-future telescope capabilities. At the least inevitable end, but still physically constrained, are electromagnetic leakage and deliberate signals. These depend on choices the civilization makes about communication technology and whether it is trying to be detected. The filter analysis suggests that civilizations which survive long enough to be otherwise detectable have probably also developed beyond the stage of careless electromagnetic leakage, either by using more efficient communication technologies or by deliberately minimizing their electromagnetic footprint for strategic reasons. Deliberate beacons, the kind that SETI has traditionally searched for, require the additional choice to transmit, which a surviving civilization may or may not make. The search for leakage in signals is therefore the weakest test of the filter hypothesis, but also the one with the most immediate relevance to questions of contact and communication. The negative results from technosignature searches to date, taken together across all these signature types, paint a consistent picture. We see no evidence of civilizations operating at type II or type III scales anywhere in the observable portion of the galaxy, and the evidence for even type I scale civilizations beyond Earth is null. The negative result is consistent with the filter hypothesis. It is also consistent with the alternative that our search sensitivity is not yet adequate, which is true for some signature types at large distances. The ongoing program is therefore to improve sensitivity and coverage until either a detection occurs or the constraints become tight enough that the silence is unambiguously informative. We are not yet at the latter point, but we are moving toward it faster than at any previous time in the search's history. The Exoplanet Atmospheric Characterization Program represents a different kind of diagnostic, one that tests not the frequency of advanced civilizations, but the frequency of biological ones. If we detect chemical biosignatures in many planetary atmospheres, this pushes the filter forward in time toward the technological threshold where our analysis locates it, which strengthens the filter hypothesis. If we detect few or no biosignatures despite adequate survey coverage and sensitivity, this suggests the filter may be earlier in the chain, at abiogenesis or the development of complex life, which would be a different kind of answer to the paradox, but would not change the basic conclusion that the filter is real. The binary outcome, biology everywhere or biology rare, is the most informative possible result from this program, and either outcome tells us something important about where in the chain the silence originates. The specific case of K218b illustrates both the promise and the difficulty of this program. This planet, a sub-Neptune roughly 9 times Earth's mass orbiting a cool M dwarf star about 120 light-years away, was the subject of claimed detections of dimethyl sulfide in its atmosphere by JWST observations in 2023. Dimethyl sulfide on Earth is produced almost exclusively by marine biological activity, which made the claim detection significant. The claim was subsequently contested on grounds of data analysis methodology, signal-to-noise, and the question of whether the planetary environment is consistent with life, rather than with exotic abiotic chemistry. The planet may be a Hycean world, with a hydrogen-rich atmosphere over a deep liquid water ocean, a planetary type without direct analog in our solar system, and whose habitability properties are not well understood. Whether it hosts life, whether the DMS detection is real, and whether DMS in its specific environment would be biological or abiotic, are all genuinely open questions. What the K218b case demonstrates is that the Atmospheric Characterization Program is producing interesting data that is hard to interpret unambiguously, which is exactly the expected condition when the measurements are at the frontier of current capability. The science is proceeding correctly. Claims are made, contested, revised, and slowly refined through the accumulation of evidence. The process is slow by the standards of urgency the filter analysis implies, but it is the right process. The nearby star systems that will be most accessible to direct imaging by future telescopes provide the most promising near-term targets for definitive atmospheric characterization. The Alpha Centauri system, at 437 light-years distance, is the closest stellar system and contains at least one small planet candidate. Proxima Centauri, the closest individual star at 424 light-years, hosts at least one planet in the habitable zone, though the habitability of Proxima b is uncertain given the star's flare activity and the planet's likely tidal locking. Barnard star at 596 light-years, Lytton star at 12, 4 light-years, and Tau Ceti at 11. 9 light-years are among the nearest systems with confirmed or candidate terrestrial planets in or near the habitable zone. These systems will be the primary targets for the proposed Habitable Worlds Observatory and similar large telescope concepts that could in principle directly image Earth-like planets around nearby stars and characterize their atmospheric spectra with enough signal-to-noise to make definitive statements about biosignatures. The timeline for these capabilities is measured in decades rather than years. The Habitable Worlds Observatory is in the concept development phase and is not expected to launch until the mid-2040s at the earliest under current planning scenarios. The Large Interferometer for Exoplanets, a proposed European concept, has a similar timeframe. These programs would, if funded and executed as planned, provide the most definitive possible test of the biosignature question around nearby stars within the working lifetimes of researchers currently in their careers. The practical question of whether the funding and political commitment will be sustained across the required development period is itself a small-scale test of whether this civilization prioritizes long-term scientific investment over short-term budgetary pressures. The filter watches with interest. In the radio domain, the Breakthrough Listen program continues to expand its coverage and improve its signal processing capabilities. The program has access to some of the most powerful radio telescopes in the world and has conducted more sensitive searches of more targets than all previous SETI programs combined. Its non-detections are among the strongest constraints yet placed on the density of powerful radio transmitters in the galactic neighborhood. The planned square-kilometer array, a multinational radio telescope project in South Africa and Australia, will when complete be orders of magnitude more sensitive than current facilities and will open qualitatively new parameter space in the radio search. The SCA will be capable of detecting airport radar emissions from a civilization 100 light-years away, which means its non-detections of such signals will genuinely constrain whether any civilization within that distance is using the kind of radar technology that our own civilization used in the mid-20th century. The combination of these advancing observational programs means that the next 2 to 3 decades will be uniquely informative about the Fermi paradox in a way that the previous 6 decades of searching were not. We will have genuine atmospheric characterization data for nearby terrestrial planets. We will have substantially tighter constraints on radio leakage from nearby stellar systems. We will have improved infrared surveys that constrain stellar engineering to greater distances and at higher sensitivity. If the silence persists across all these advancing search modalities, the case for the filter will become significantly stronger on purely astronomical grounds. If detections occur in any category, the implications for the filter's location will need to be carefully worked out. The next 3 decades of astronomical observation are the most important period in the history of the search. This observational timeline interacts with the civilizational risk timeline in a way that is worth making explicit. The period during which we will have the most informative astronomical data about the filter's location is also the period during which the AI risk is likely to reach its most acute phase, and during which the climate system will either have passed key tipping points or not. The late 2020s through the 2040s are therefore simultaneously the most informative period for the filter analysis and the most critical period for the civilizational decisions that will determine whether this civilization is a filter survivor or a filter casualty. We will be learning more about what usually happens to civilizations like us at the same time that we are determining what will happen to us. The parallel is not coincidental. It is a structural feature of the technological moment we occupy. The philosophers who have engaged most deeply with the Fermi paradox have identified a dimension of the problem that the scientific literature tends to underemphasize: the question of what the silence implies about the nature of intelligence itself, not just about the frequency of civilizations. If intelligence reliably self-terminates at the technological threshold, this tells us something important about whether intelligence, as a phenomenon, is oriented toward long-term flourishing or toward short-term optimization. Intelligence that produces increasingly powerful technology without the corresponding wisdom to manage that technology is not functioning as an adaptive strategy in the evolutionary sense. It is functioning as a complexity trap, a feature that increases fitness in the short term by enabling competitive advantage against simpler organisms and civilizations, while decreasing fitness in the long term by generating risks that the possessing organism or civilization cannot manage. This framing is important because it suggests that the filter is not primarily about external threats or unlucky accidents. It is about the internal dynamics of intelligence itself as a feature of complex systems. Intelligence is extraordinarily effective at solving immediate, well-defined problems. It is much less effective at managing the second and third-order consequences of its own solutions, especially when those consequences are diffuse, long-term, and require coordination rather than individual action. The filter exploits the second property against the first. Civilizations that develop intelligence get very good at building powerful things very quickly, and then encounter problems that their intelligence, without the corresponding institutional and cultural wisdom, cannot adequately manage. The gap between solving immediate problems and managing their long-term consequences is the gap the filter occupies. Understanding intelligence this way also illuminates why the development of artificial intelligence represents such a specific and acute filter risk. Artificial intelligence, at its most capable, is intelligence optimized for immediate problem-solving without the evolutionary and cultural history that gave biological intelligence whatever wisdom it possesses. An AI system can be extraordinarily capable at solving defined problems while being entirely without the kind of long-term, second-order consequence management that wisdom involves. Deploying systems with this property in domains where second-order consequences matter enormously, which is to say all of the domains that existential risks involve, is a way of concentrating the most dangerous aspect of the intelligence-wisdom gap into systems that operate faster than human institutional response. The filter sees artificial intelligence as the purest possible instantiation of the problem it is designed to exploit. The corrective to this dynamic, if there is one, is the development of what might be called civilizational wisdom, the capacity to manage the second-order consequences of intelligence at the speed and scale at which intelligence generates them. This is not the same as individual human wisdom, which is valuable but insufficient at civilizational scale. Civilizational wisdom is an emergent property of the institutional, cultural, and governance systems that a civilization develops to coordinate collective action across time and space. It includes the ability to represent future generations in present decision-making, the ability to coordinate across competing national interests around shared existential concerns, the ability to manage technological development at a pace consistent with adequate governance, and the ability to maintain long-term institutional commitments against the pressure of short-term political and economic incentives. These capacities exist in embryonic form in current human institutions. They have not yet been developed to the scale and reliability that the filter requires. The task of civilizational survival is the task of developing them fast enough. The deepest reason this is so difficult is that civilizational wisdom is not just a technical or institutional problem. It is a problem of collective identity, of whether a civilization conceives of itself as a temporary extraction enterprise on a finite planet or as a long-term stewardship project with obligations to both the past and the future. Civilizations that conceive of themselves as extraction enterprises make decisions that are rational within that frame, but that systematically underinvest in long-term sustainability. Civilizations that conceive of themselves as stewardship projects make different decisions, ones that discount the future less severely, that weight the welfare of future generations more heavily, and that treat the natural and institutional systems they inherit as resources to be maintained rather than consumed. The shift from an extraction frame to a stewardship frame is ultimately a cultural and philosophical task, not primarily a technical or political one. It requires changing the stories a civilization tells about itself, the values it teaches to its children, the metrics by which it measures success, and the scope of moral community for whose welfare it takes responsibility. These changes are possible. They are slow. The filter is faster. The question of whether this civilization will make the required shift in time is genuinely open. There are genuine grounds for concern. The dominant economic ideology, the political dynamics of short electoral cycles, the information ecosystem that prioritizes engagement over accuracy, and the competitive dynamics between great powers that prevent the coordination the risks require, all point in the direction of insufficient response. There are also genuine grounds for hope. The rapid growth of the existential risk research community, the increasing political salience of AI safety, the remarkable cost reductions in clean energy technology, the surviving arms control institutions even in their weakened state, and the demonstrated human capacity for rapid learning and adaptation when the situation becomes sufficiently clear and sufficiently urgent. Whether the grounds for hope outweigh the grounds for concern is not a question the astronomical evidence can answer. The astronomical evidence says only what the typical outcome is. It says that hope has not been enough for most civilizations in this situation. It does not say that hope is insufficient in principle. It does not say that our civilization cannot be different. It says that being different requires being deliberately and urgently different in ways that are well understood but not yet adequately implemented. The silence is not a verdict. It is a warning with a known remedy and an uncertain timeline. The investigation has now covered the full territory it set out to cover. The silence has been measured and confirmed across multiple observational modalities. The hypotheses have been tested and most have been found insufficient. The filter has been located at the technological threshold. Its mechanisms have been described in detail: nuclear weapons, biological weapons, AI misalignment, ecological destabilization, and information system fragmentation. The behavioral dynamics that make the filter effective have been examined: the structural gap between intelligence and wisdom, the collective action problems that prevent adequate coordination, the political economy that consistently underinvests in long-term existential risk management, and the cognitive architecture that makes long-term thinking difficult for individual actors. The institutional innovations required to overcome these dynamics have been identified. The specific indicators that measure our current trajectory toward or away from filter survival have been assessed, and the deeper philosophical dimensions of the challenge have been articulated: the nature of intelligence as a potential complexity trap, the distinction between civilizational intelligence and civilizational wisdom, and the cultural and philosophical shift required to move from an extraction frame to a stewardship frame. What emerges from the full investigation is not a comfortable picture. It is an accurate one. The silence of the sky is telling us something specific immediate, and important about the typical fate of civilizations that reach our level of technological capability. The message is not that we are doomed. The message is that the default trajectory leads to doom, and that changing the trajectory requires deliberate, urgent, large-scale effort of the kind that is not currently underway at adequate scale. The message is that the Fermi paradox, properly understood, is the most important piece of scientific evidence we have about our own future, more directly relevant to civilizational decisions than any other result in the history of astronomy. The silence continues. The sky remains quiet. The search goes on, and somewhere in the space between the math that says the sky should be loud and the instruments that say it is not, the specific shape of our civilizational challenge becomes visible, not as an abstraction, not as a philosophical puzzle. As a description of what is happening right now, on this planet, in this decade, among the people who are alive to read this conclusion and to decide what to do with it. That decision is the only part of the investigation that the investigation itself cannot complete. The astronomy can measure the silence. The logic can locate the filter. The policy analysis can identify the required response. The philosophy can articulate the required cultural shift. But the actual choices that will determine whether this civilization is a filter survivor or a filter casualty are made by people, in institutions, responding to incentives, under conditions of uncertainty, with the full complexity of human motivation and human fallibility. The cosmos has been quiet for billions of years. The next few decades will contribute a small but specific piece of data to that silence, either the continuation of the quiet or its eventual interruption by the signals of a civilization that found a way through. Which piece of data we contribute is being determined now. The investigation is complete. What happens next is not yet written. The investigation has built its case across 4 extensive sections. The silence has been measured, the hypotheses tested, the filter located, the mechanisms described, the policy implications drawn out, and the philosophical dimensions examined. What remains is the territory that most treatments of the Fermi paradox never reach, not because it is beyond the scope of the question, but because it requires holding simultaneously the full weight of everything that has come before, while pushing further into the specific details that transform a general conclusion into a complete picture. This final section undertakes that remaining work. It examines the specific civilizational developments of the early 21st century that are most directly relevant to filter survival, the emerging understanding of how other civilizations might have navigated or failed to navigate analogous challenges, the specific research programs that are most important for both understanding and responding to the paradox. And the ultimate question that the Fermi analysis poses not just to scientists and policymakers, but to every person alive at this particular moment in the history of this particular civilization. Start with the temporal specificity of the current moment, because the filter analysis is not uniformly distributed across time, and the current period has specific characteristics that make it more acute than any previous period in our civilization's history. The first half of the 20th century was dangerous. The development of nuclear weapons, the 2 world wars, the totalitarian experiments of fascism and Stalinism represented genuine filter pressure on our civilization. But the filter pressure was limited by the technological capability available. Nuclear weapons were devastating, but required nation-state resources to build. Biological weapons programs were large and costly. The information systems that shaped political decision-making were centralized enough that scientific consensus could be communicated with some reliability through established institutional channels. The scale of harm available to small groups was limited by the technology of the era. The filter was real, but the specific mechanisms available to it were constrained. The second half of the 20th century added the hydrogen bomb, the intercontinental ballistic missile, and the early stages of genetic engineering, expanding the filter's toolkit considerably. But it also produced the most successful period of international institutional development in history: the United Nations system, the arms control treaties, the international financial institutions, the scientific bodies, the public health frameworks. The filter pressure rose, but so did the institutional response. The Cold War came terrifyingly close to ending the experiment on multiple occasions, but it did not. And by the end of the century, there were genuine grounds for cautious optimism about the direction of travel. The early 21st century has seen a qualitative change in the nature of the filter pressure that is not simply a continuation of previous trends. 3 developments have converged in ways that are without precedent in our civilizational history, and that collectively represent the most acute concentration of filter pressure we have yet faced. The first is the democratization of catastrophic capability. The cost of synthesizing DNA has fallen by a factor of roughly 1 million since the human genome was first sequenced. The capability to design and synthesize novel biological agents is now accessible to small research teams rather than to state programs with large budgets and specialized infrastructure. The computing power required to train AI systems capable of accelerating biological design is becoming increasingly accessible. The convergence of synthetic biology, AI, and declining hardware costs means that within the next decade or two, the capability to design and produce potentially pandemic-level pathogens may be accessible to groups of tens rather than thousands of people, and possibly to individuals with sufficient expertise. No governance framework in the world is currently adequate to manage this risk at that scale of distribution. The filter has never previously had access to this specific dynamic, catastrophic capability at an unprecedented rate of diffusion into an increasingly large pool of potential actors. The second unprecedented development is the real-time globalization of information in a form optimized for emotional engagement rather than accuracy. Previous periods of civilizational crisis were managed, imperfectly, through information systems that maintained some degree of separation between expert consensus and public opinion, not because experts were infallible, but because the institutional filters between technical knowledge and public discourse allowed some degree of translation and quality control. The current information ecosystem has largely dissolved those filters. Social media platforms with billions of users are governed by engagement algorithms that systematically elevate emotionally resonant content over accurate content. The result is an information environment in which scientific consensus on existential risks is routinely challenged, distorted, and undermined by content that is more emotionally engaging but less accurate, and in which the political mobilization of large populations against effective existential risk management is structurally enabled by the platforms that dominate public discourse. This is a genuinely new filter mechanism that was not present in previous periods of civilizational crisis. The filter has never previously had access to global-scale information systems that are structurally optimized to undermine the collective deliberation on which adequate crisis response depends. The third unprecedented development is the specific nature of advanced AI as both a risk amplifier and an independent risk. Previous technologies, including nuclear weapons and biotechnology, were powerful but static in the sense that their capability trajectories were relatively predictable and their governance challenges, while severe, were bounded. A nuclear weapon is a weapon. Its capabilities are large but defined. A sufficiently advanced AI system is not bounded in the same way. It is a general-purpose tool for accelerating capability development across all domains, which means it can accelerate the development of biological weapons, cyber weapons, financial manipulation tools, and influence operations simultaneously, while also posing its own direct risks through misalignment. The cross-domain amplification effect of advanced AI is without precedent in the history of transformative technologies. The filter has never previously had access to a technology that can simultaneously accelerate every other risk category while also constituting an independent existential risk. The current period is therefore not merely a continuation of the filter pressure of previous decades. It represents a qualitative threshold in that pressure, one that the existing institutional architecture is much less well adapted to than it was to the nuclear and biological risks of the previous century. These three developments, the democratization of catastrophic capability, the emergence of engagement-optimized global information systems, and advanced AI as a cross-domain risk amplifier, define the specific character of the current filter pressure. They interact with each other in ways that compound the challenge. AI accelerates the diffusion of catastrophic biological capability by reducing the expertise required for advanced protein design and pathogen engineering. Engagement-optimized information systems undermine the political will for biosecurity investment by making the diffuse probabilistic risks of engineered pandemics less politically salient than immediate emotionally engaging content. Advanced AI systems trained on low-quality information may themselves propagate and amplify inaccurate content, further degrading the informational basis for collective decision-making. The specific combination of these three developments is unique to the current moment and constitutes a filter pressure that the institutional architecture of the 20th century is not adequate to manage. Understanding this specificity is important because it implies that the required response is not simply doing more of what we did in the 20th century. The arms control frameworks, the public health institutions, the scientific advisory bodies, and the international coordination mechanisms that partially manage the filter risks of the previous century need to be supplemented by fundamentally new institutional designs adapted to the specific character of current filter pressure. This includes governance mechanisms for advanced AI that can operate at the speed of technological development rather than at the speed of legislative processes. It includes information ecosystem redesign that creates institutional pressures for accuracy and long-term consequence orientation rather than for engagement and emotional resonance. It includes biosecurity infrastructure that can detect and respond to novel engineered threats at the speed that synthetic biology development enables. And it includes the development of new international coordination mechanisms that can function effectively in the current period of great power competition, rather than requiring the kind of cooperative international environment that existed briefly in the immediate post-Cold War period. None of these are small tasks. All of them are being worked on by competent researchers and practitioners with genuine commitment. The question that the filter analysis forces is whether the pace of institutional innovation is fast enough relative to the pace of the technological developments it needs to manage. The honest current assessment is that it is not. The gap between technological capability and governance capacity is wider now than it has been at any previous point in our civilizational history, and the trajectory of that gap is toward widening further rather than closing. This is the specific quantitative statement that the filter analysis makes about our current moment. Not that failure is certain, but that the current rate of governance innovation is insufficient relative to the current rate of technological development, and that closing the gap requires a significant acceleration of institutional innovation that is not currently underway. The researchers who have spent the most time thinking about this problem tend to converge on a specific set of priorities, ordered by urgency and by the magnitude of potential harm. The ordering is not universally agreed upon, but the broad outlines of the priority list are relatively stable across serious analysts of existential risk. Artificial intelligence alignment and governance ranks as the most urgent priority by most analysts because of the combination of speed, cross-domain impact, and the specific nature of the alignment risk. The speed is the critical factor, the timeline from current frontier capabilities to capabilities that could constitute an existential risk if inadequately aligned is measured in years to decades by most serious researchers, with genuine uncertainty about whether it is closer to years or closer to decades. This is an extraordinarily short planning horizon for institutional innovation of the required scope. The governance mechanisms that need to be in place before frontier AI systems reach concerning capability levels need to begin being built now, before those capability levels are reached, because building adequate governance after the fact is much harder than building it before. The specific institutional innovations required include international agreements on capability thresholds that trigger mandatory safety evaluation before deployment, shared technical standards for alignment verification, mechanisms for monitoring compliance across competitive AI developers, and crisis response protocols for misalignment events of varying severity. All of these are technically and politically feasible. None of them currently exist in adequate form. Biosecurity ranks second in urgency by most analysts, elevated from its previous ranking by the combination of the COVID-19 experience, which demonstrated both the scale of damage that naturally occurring pandemics can cause and the inadequacy of current international response mechanisms, and the accelerating capability trajectory of synthetic biology. The specific priorities in this domain include upgrading global pathogen surveillance infrastructure to provide genuine real-time monitoring of novel dangerous agents, strengthening the verification mechanisms for the Biological Weapons Convention to provide at least partial confidence that state biological weapons programs are not operating in violation of the treaty. Establishing international governance mechanisms for dual-use biological research that can balance the enormous beneficial value of synthetic biology against the catastrophic potential of its misuse, and building rapid response manufacturing capacity for medical countermeasures that can be deployed at the speed that emerging biological threats require. The financial requirements for this agenda are substantial but modest compared to global defense spending. The political obstacles are more significant than the financial ones. Biosecurity investment requires sustained political commitment across electoral cycles and international cooperation across geopolitical divisions that are currently severe. Nuclear risk management ranks third in urgency, not because the risk is less severe, but because the institutional infrastructure for managing it is more developed than for AI or biosecurity risks, and because the pace of change in the risk landscape is somewhat slower. The specific priorities include reviving and strengthening the arms control architecture that has been allowed to erode since the end of the Cold War, developing new verification mechanisms and coordination frameworks that can accommodate the multipolar nuclear environment that has replaced the Cold War's bipolar structure. Accelerating the development of crisis communication mechanisms between nuclear powers that can function in the compressed decision timescales that modern delivery systems create, and maintaining and strengthening the political commitment to the long-term goal of nuclear abolition that provides the normative framework within which arms reduction steps can be justified domestically in nuclear states. Obstacles are primarily political and strategic. Great power competition makes nuclear cooperation difficult. Domestic political economies in nuclear states resist disarmament, and the verification challenges for nuclear abolition are genuine even if technically manageable with adequate political will. The current trend is negative on most of these dimensions, which places nuclear risk management in the category of urgent but manageable, rather than acute if current trends continue. Climate and ecological stabilization ranks fourth in terms of immediate urgency, not because the long-term threat is less severe, but because the timeline for the most severe consequences is somewhat longer, and because the pace of progress in clean energy technology has improved the near-term outlook relative to pessimistic scenarios of a decade ago. The specific priorities include accelerating the global clean energy transition at a pace consistent with limiting warming to below levels that trigger the most severe tipping point dynamics, establishing effective international mechanisms for forest protection and carbon sequestration at the scale required to complement emissions reductions, building climate adaptation infrastructure in the most vulnerable regions before the consequences of committed warming overwhelm the capacity to adapt, and integrating biodiversity protection into the climate policy framework in ways that recognize the dependence of climate stability on functional ecosystems. The financial requirements for this agenda are large, measured in trillions of dollars annually globally, but they are economically manageable relative to global GDP and comparable to historical infrastructure investment programs. The political obstacles are primarily the political economy of stranded fossil fuel assets and the equity dimensions of asking developing nations to forego the industrialization pathway that wealthy nations used while contributing less to the problem. Information ecosystem reform is the least well-developed item on the priority list in terms of institutional understanding and political will, yet it is in some ways the most foundational because it affects the political capacity to address all the other risks. The specific challenge is that the dominant information platforms are private corporations with fiduciary obligations to shareholders that are often in tension with the public interest in accurate, consequence-oriented information. Regulatory approaches to this challenge face significant constitutional and jurisdictional obstacles in many democratic nations, where freedom of expression protections limit the degree to which governments can mandate content standards without creating censorship risks. The alternative of redesigning platform incentive structures through liability regimes, algorithmic transparency requirements, or structural separation of content curation from revenue generation is more promising, but faces intense lobbying resistance from the affected industries. The fundamental challenge is that the information ecosystem problem is both highly technically complex and deeply politically contested, which makes it harder to address than problems that are technically complex but politically tractable, like clean energy deployment, or politically contested but technically straightforward, like arms control verification. The multiplanetary priority is the longest-term item on the list, and the one most directly targeted at reducing the single point of failure vulnerability that makes filter events terminal rather than survivable. The development of genuine self-sustaining human settlements beyond Earth represents a qualitative change in civilizational resilience because it creates the possibility of recovery from civilizational catastrophe rather than requiring that every catastrophe be prevented. The current pace of space development, driven primarily by the commercial sector in the United States and by national programs in China and elsewhere, is faster than at any point since the Apollo era and is producing genuine capability advances in launch economics, orbital operations, and near-term lunar exploration. The gap between current capability and genuine planetary self-sufficiency is still enormous, requiring developments in closed-loop life support, food production in space, manufacturing from in situ resources, and the development of autonomous institutional capacity that can maintain a settlement without regular resupply from Earth. These developments are achievable within realistic technological and economic projections. They require sustained commitment across the timescales, decades to centuries, that multiplanetary settlement requires. The filter analysis supports treating this investment as foundational rather than aspirational, because the expected value calculation changes dramatically when civilizational extinction is on the probability distribution. The research priorities in existential risk are equally important to the policy priorities, because the policy priorities depend on technical and institutional understanding that the research must provide. The alignment research agenda includes interpretability, the development of tools for understanding why AI systems produce specific outputs; robustness, ensuring that systems behave as intended under distribution shift and adversarial inputs; scalable oversight, developing methods for evaluating the behavior of systems more capable than the evaluators; and governance mechanisms for monitoring and regulating AI development across competitive actors. Each of these research areas is active, each is producing genuine progress, and each is severely underfunded relative to the capability development it needs to keep pace with. The ratio of safety research investment to capability research investment in the leading AI organizations is typically estimated at less than 10% and often much less. Changing that ratio is both the most important near-term policy lever for AI risk management and the one most resistant to change given competitive dynamics. The biosecurity research agenda includes the development of platform technologies for rapid countermeasure production that can be deployed faster than novel pathogens spread, the design of pathogen surveillance systems that can detect novel agents before they reach pandemic levels, the development of personal protective equipment and environmental controls that can provide adequate protection before specific countermeasures are available, and the study of governance mechanisms that can balance openness in biological research with adequate security measures. The pandemic response research mobilized by COVID-19 has advanced some of these areas significantly, particularly mRNA vaccine platform technology and genomic surveillance. The research on engineered pathogen risks and the specific governance mechanisms required to manage them remains underdeveloped relative to the urgency of the challenge. The nuclear security research agenda includes the development of improved verification technologies that could support more comprehensive arms reduction agreements, the study of nuclear risk dynamics in multipolar deterrence environments, the analysis of decision-making under crisis conditions in nuclear states, and the development of crisis communication and risk reduction mechanisms adapted to modern delivery system capabilities and decision timescales. The academic research community working on these questions is small relative to the importance of the topic and faces significant challenges accessing the classified information and government decision-making contexts that would make the research most useful. The climate and ecological research agenda is the most mature of the filter-relevant research areas, with the IPCC providing the most comprehensive ongoing synthesis of existential risk research in any domain. The remaining research priorities include improved understanding of tipping point dynamics and their interaction, better models of the economic and social consequences of various warming scenarios, the development of carbon removal technologies that can be deployed at scale if emissions reductions prove insufficient, and the governance mechanisms for managing large-scale climate intervention options like stratospheric aerosol injection that may become relevant as mitigation falls short of what is required. Across all these research areas, the common challenge is translating technical findings into policy action at the speed and scale the risks require. This translation problem is not primarily a communication challenge, though better scientific communication is important. It is a governance challenge. The institutions that need to act on the research findings are not designed to process and respond to rapidly evolving technical knowledge across multiple simultaneously urgent domains. The governance innovation required is itself a research challenge, drawing on political science, institutional economics, complex systems theory, and historical analysis of how societies have successfully navigated previous large-scale coordination challenges. The specific question of how civilizations navigate filter events is itself a legitimate research topic, even though we have only one civilization to study directly. The indirect evidence comes from the pattern of extinctions and civilizational collapses in human history, from the game-theoretic analysis of collective action problems, from the anthropological study of how societies have managed common pool resources, and from the historical analysis of how international institutions have formed and functioned. These indirect sources are not as informative as direct evidence from other civilizations would be, but they are not nothing. They provide a basis for identifying which institutional designs have historically been more successful at managing collective action problems at large scales, and for inferring which features of those designs might be relevant to the specific challenges of existential risk management. The historical record on collective action around existential threats is more mixed than either pessimists or optimists typically acknowledge. The pessimists are right that most large-scale collective action challenges have been inadequately managed until they produced significant harm. The optimists are right that some have been managed successfully, and that the capacity for successful management has generally increased over time as institutional learning has accumulated. The filter's effectiveness appears to depend on whether the pace of institutional learning is fast enough relative to the pace of technological development. In previous eras, the pace of technological development was slow enough that institutional learning could at least partially keep up, however imperfectly. The specific character of the current period, with AI accelerating technological development across all domains simultaneously, is that the pace of technological development may be outrunning institutional learning capacity in a qualitatively new way. This is the most specific reason why the current filter pressure is more acute than previous periods. The research on civilizational resilience more broadly, on what makes societies capable of absorbing large shocks and recovering rather than collapsing, is also directly relevant. The comparative study of how different societies have responded to environmental pressures, resource constraints, and technological disruptions provides some insight into the features of social organization that predict resilience. These include the maintenance of diverse, redundant institutional structures that prevent single points of failure, the cultivation of social capital and trust that enables rapid coordination in crisis, the development of cultural practices that maintain long-term thinking in the presence of short-term pressure, and the institutional mechanisms that prevent the concentration of power that reduces adaptability. None of these features are automatically present in industrial civilizations, and several of them are actively being eroded by the dynamics of the current information environment and political economy. Building and maintaining civilizational resilience, alongside the more specific existential risk management programs, is therefore an important part of the overall strategy for filter survival. The question of what civilizations that do survive the filter look like, and what their trajectory beyond the filter involves, is necessarily speculative given that we have no confirmed examples. But the speculation can be constrained by physics and by the logic of what durable civilizations require. A civilization that survives the filter must have developed some form of effective global governance for existential risks, because the risks do not disappear once the immediate filter event is navigated. New technological capabilities will continue to generate new risks, and the governance architecture required to manage them must be able to evolve as the technological landscape evolves. A civilization that survives the nuclear filter but then develops unmanaged bioweapons capability, or that survives the bioweapons filter but then deploys misaligned AI, is not a filter survivor in the full sense. Genuine filter survival requires the development of durable institutional capacity for managing the class of existential risks that technological civilization generates, not just the specific instances of that class that are currently most salient. A civilization that develops this capacity would also, almost certainly, develop multiplanetary presence, because the existential risk framework that justifies managing terrestrial risks also justifies reducing single-planet vulnerability. The same institutional wisdom that enables effective global governance of nuclear weapons also enables long-term multi-generational planning for space settlement. The same cultural orientation toward long-term stewardship that supports climate stabilization also supports investment in the centuries-long project of planetary settlement. Filter survival and multiplanetary expansion are not separate projects. They are manifestations of the same civilizational orientation toward long-term flourishing. The energy trajectory of a filter-surviving civilization is also physically constrained. A civilization that has solved the governance challenges of managing its home planet and has begun expanding to other planets will use energy at scales far exceeding current levels. The physical constraints on energy use at those scales are the constraints of thermodynamics. Energy must come from somewhere, and the most abundant sources at stellar scales are the stars themselves. A civilization that has been operating at filter-surviving levels for millions of years would likely have developed energy systems that approach the theoretical limits of efficiency for harvesting stellar output. The infrared signature of such a civilization would depend on the specific design of its energy systems and on its choices about waste heat management, but at sufficiently large scales, the signature should be detectable with instruments of appropriate sensitivity. The absence of such signatures in current surveys is consistent with the filter hypothesis. Surviving civilizations are either very rare, or very recent, or very deliberately quiet in ways that extend even to waste heat management at unprecedented efficiency levels. The deliberate quiet option deserves the most careful examination at this stage of the investigation, because it is the one that introduces the most uncertainty into the interpretation of the silence. If some civilizations survive the filter and develop to Kardashev type II or type III scales, while deliberately managing their electromagnetic and infrared signatures to prevent detection, the silence becomes much harder to interpret. A civilization that has been operating at stellar scales for millions of years could, in principle, develop radiative camouflage technologies that make its waste heat indistinguishable from natural astrophysical sources. It could use frequencies and modalities for internal communication that do not produce detectable leakage. It could engineer its stellar systems to mimic natural spectral energy distributions, even while extracting large fractions of the stellar output. If such camouflage is both feasible and routinely chosen by surviving civilizations, our current surveys could be embedded in a galaxy full of mature civilizations without detecting any of them. The dark forest hypothesis is the most developed version of this argument, as we have already examined. Its specific claim that the camouflage is a strategic response to an environment of mutual predation faces the observational and logical challenges discussed in earlier sections. But the more general claim that mature civilizations might choose to manage their observable signatures for reasons that do not necessarily involve predation is harder to dismiss. A civilization that understands the filter might choose to minimize its observable presence precisely because it understands that being detectable during a civilization's early technological period is potentially dangerous, whether from predation, from the attention of misaligned AI systems created by other civilizations, or from the disruptive effects of contact on younger civilizations still navigating their own filter events. The ethical argument for concealment from civilizations in their filter period is not obviously weaker than the ethical argument for contact. If the filter is real, and if contact with an advanced civilization during the filter period would be destabilizing, the most ethical behavior by mature civilizations might be exactly the silence we observe. This interpretation is uncomfortable because it is essentially unfalsifiable with current technology. A galaxy full of deliberately quiet mature civilizations is indistinguishable from a galaxy empty of them, at least until our detection capabilities exceed whatever camouflage techniques the civilizations employ. The only distinguishing test would be finding a signature that is too well camouflaged to be natural, a source that is clearly engineered but that would require advanced technology to produce in such a natural-appearing form. This is a genuinely paradoxical search target. We would need to find evidence of concealment, which requires either accidental disclosure or a level of detection capability that exceeds the concealment capability. Neither is achievable with current technology, and the timeline for achieving either is uncertain. The silence therefore remains genuinely ambiguous between three broad interpretations. Either the galaxy is mostly empty of mature civilizations because the filter eliminates them, or the galaxy contains mature civilizations that are deliberately quiet for reasons we can partially infer but not confirm. Or the galaxy contains mature civilizations that are neither broadcasting nor particularly trying to conceal themselves, but whose presence we cannot detect because our instruments and our search strategies are not yet sensitive or comprehensive enough. The first interpretation has the most explanatory power given the full body of evidence and requires the fewest additional assumptions. The second is possible but introduces unfalsifiable elements. The third is possible for some signature types but is increasingly constrained as our surveys improve. The investigation has now reached the point at which the remaining work is not adding new analytical content but deepening the examination of implications that have already been established. The silence is real. The filter is the most defensible explanation. The filter is located at the technological threshold. We are at the technological threshold. The implications for our civilizational priorities are clear. The current trajectory is insufficient. The required course corrections are known. The political and institutional obstacles are large but not insuperable. The astronomical evidence will continue to improve. The civilizational decisions that will determine the outcome are being made now. What remains to be done in this final section is to address the question that the investigation has been building toward throughout its entire length. not what the Fermi paradox means for our understanding of the universe, but what it means for us, individually and collectively, as members of the civilization that the paradox is most directly about. The Fermi paradox has a specific character as a piece of evidence that distinguishes it from most other scientific findings. Most scientific findings are about things that are remote from immediate human experience: the behavior of subatomic particles, the dynamics of distant galaxies, the chemistry of ancient rocks. They are interesting and important, but they do not make a direct claim about the situation of the person receiving the information. The Fermi analysis, properly completed, makes exactly this kind of direct claim. It says that you, the person processing this information, are living inside the most important civilizational moment in the history of this particular experiment in intelligence. It says that the decisions made by your civilization, in your lifetime, will be among the most consequential decisions ever made by any civilization, not because of their scope in the everyday sense, but because of their specific relevance to whether this civilization contributes another data point to the silence or becomes the first local exception. This is an extraordinary claim. It deserves examination rather than acceptance or dismissal. Is it accurate that the current period is uniquely important in this sense? The filter analysis suggests that it is, for the specific reason that the technological developments of the current period are reaching the threshold at which the filter operates, and are doing so in a compressed timeframe that reduces the opportunity for the kind of gradual institutional adaptation that previous technological transitions allowed. The nuclear period was filter-relevant, but unfolded over decades in a bipolar international environment with relatively clear lines of deterrence and relatively stable institutional structures. The current period involves AI, biosecurity, climate, and information system risks converging simultaneously in a multipolar international environment with weakening institutional structures. The temporal density of filter pressure is higher now than it has been at any previous point, and the institutional capacity to respond is not keeping pace. If this assessment is accurate, then the practical implication is that the current period is one in which individual choices about engagement with existential risk have higher expected value than at most other periods in history. This is counterintuitive because individual humans feel small relative to civilizational scale challenges, and the appropriate response to feeling small relative to large challenges is often to disengage rather than to engage. The filter analysis argues against disengagement on purely probabilistic grounds. If the filter's effectiveness depends in part on the collective disengagement of individuals who understand the risks, but conclude that their contribution is too small to matter, then the individual choice to engage rather than disengage is a specific form of behavior that the filter cannot rely on. Civilizations that develop a culture of engaged, informed, long-term oriented citizenship are specifically the ones that the filter analysis identifies as having better survival probabilities. The specific forms of engagement that the filter analysis supports are not romantic or abstract. They are concrete and measurable. Supporting and participating in governance processes that create binding international frameworks for AI safety, biosecurity, nuclear risk reduction, and climate stabilization. Consuming and sharing information about existential risks in ways that favor accuracy over emotional engagement, thereby contributing to rather than degrading the informational basis for collective decision-making. Supporting the research programs and the researchers working on alignment, biosecurity, arms control, and existential risk more broadly, through funding, through career choices, through public advocacy. Developing and modeling the long-term thinking and the commitment to future generations that the cultural shift from extraction to stewardship requires. These are not grand heroic acts. They are the ordinary civic behaviors of a civilization that has internalized what its own astronomical evidence is telling it. The most important of these behaviors, for those who have the relevant expertise and the career flexibility to act on it, is direct engagement with the most urgent risk reduction work. The AI alignment problem needs more researchers. The biosecurity governance challenge needs more policy analysts with technical expertise. The nuclear arms control agenda needs more specialists in verification technology and strategic studies. The climate policy agenda needs more people who understand both the technical and the political dimensions of the required transformation. The information ecosystem reform agenda needs more researchers who understand both the technical architecture of platforms and the political economy of media regulation. Each of these areas is critically understaffed relative to its importance, and the marginal value of additional expertise is high. For individuals who are considering career choices, the filter analysis provides a clear framework for evaluating the expected impact of different trajectories. Fields directly relevant to existential risk reduction have higher expected civilizational impact than most other career paths, by margins that are not small. The astronomical research agenda is itself a form of engagement with the filter question, and it deserves recognition as such. Researchers working on exoplanet atmospheric characterization, on techno-signature detection, on the statistical analysis of stellar populations for signs of engineering, and on the theoretical development of the filter hypothesis are contributing to our understanding of what the silence means and what it requires. Better understanding of the filter's location and mechanisms is actionable knowledge. Every paper that clarifies whether the biological steps are easy or hard, every survey that constrains the density of engineered infrared sources, every analysis that improves our estimate of where in the chain the silence originates, is a contribution to the most important scientific investigation in the history of our civilization. The funding and institutional support for this research is modest relative to its importance, and increasing it is a legitimate and high-impact form of engagement with the filter question. The educational dimension is equally important and perhaps the most scalable form of engagement available to most people. A civilization that broadly understands the Fermi paradox in its full form, not as an interesting puzzle about alien civilizations, but as a diagnostic tool for understanding civilizational risk, is a civilization that is better equipped to make the collective choices that filter survival requires. The filter's effectiveness depends in part on collective ignorance of its nature and implications. Civilizations that understand the filter can act on that understanding in ways that specifically counteract the mechanisms the filter exploits. Education about the Fermi paradox, about existential risk, about the history of collective action around large-scale threats, about the institutional innovations that successful responses have required, and about the specific current trajectory of civilizational risk, is therefore a form of filter intervention that scales with the number of people who receive and act on the education. This is ultimately what makes the Fermi paradox important in a way that goes beyond its scientific interest. It is not just a question about whether we are alone in the universe. It is a question about what being alone means and what it implies. If we are alone because the filter has eliminated most civilizations, then we are surrounded by the statistical evidence of what happens when intelligence fails to develop the wisdom to manage its own power. If we are the first intelligence to survive the filter in our galactic neighborhood, then everything about who we become and what we build will define the character of intelligence in this region of the universe for an extraordinary span of time. The stakes of that responsibility are difficult to fully internalize, and perhaps they should not be fully internalized because the psychological weight would be paralyzing. But they should be partially internalized, enough to change the priority ordering of civilizational decisions, enough to make existential risk management a first-order concern rather than a second-order one, and enough to motivate the kind of sustained collective action that the filter requires to be defeated. The sky has been quiet for as long as we have been able to listen to it. The silence is not nothing, it is data. It is the most comprehensive dataset we have about the typical fate of technological civilizations, and it says that the typical fate is silence. The investigation has built the case for this conclusion carefully and completely. The conclusion stands. The sky is quiet because intelligence usually fails at the threshold we now occupy. The threshold is not a wall. It is a test. The test is whether a species that is intelligent enough to build the instruments that reveal the silence is also wise enough to understand what the silence is telling it and to act on that understanding before the window closes. The window is open. The instruments are built. The silence has been measured. The message has been received. What happens next depends on what we do with it. The cosmos will continue to expand. The stars will continue to burn. The galaxy will continue to turn on its ancient axis, indifferent to the small blue world in one of its outer spiral arms where, for a brief and remarkable period, intelligence arose and looked outward and asked the deepest possible question about its place in the universe and its prospects for the future. The answer to that question is written in the silence. The response to the answer is written in what we do next. The investigation is complete. The silence has spoken. The rest is up to us.